try, but for me it's impossible to use it because now that I'm getting older, if I need to look at something close, I need to take out my glasses, and if I look far away, so I will probably just use the screen without looking at the monitor, because otherwise, or otherwise I take out glasses and I will see a monitor, so the screen, but blurred a little bit.
Yes, same for me, I mean.
Yeah, there's a point.
So you don't care where this is.
Good morning. Welcome to the second day of Metis workshop. So it's 9, so we'll start. The first presenter is Irmela, who will talk about vector value probabilistic seismic hazard analysis.
And about the investigation to use vector-valued analysis, which for risk assessments, which implies the development of vector-valued PSHA. This is a work that has been done with colleagues from EDF and also colleagues from the Metis project, Marco, Georgios, and Paolo. First of all, let me start with some general introduction. For those who might not be aware of it, what is vector PSHA? It consists simply in considering more than one intensity measure in the PSHA computations to account for the correlations between the intensity measures, because if you consider in the hazard analysis each intensity measure one after the other, you cannot directly introduce a correlation between the intensity measures. Yes, okay, and why might we want to do this? It could be used in a framework for risk assessment with more than one intensity measure. In general, now today we use one intensity measure. For example, in nuclear we use the PGA, but we could, in several cases, and I will come back to that later on, where and why this could be of interest, use more than one intensity measure for the fragility and the hazard computations. So, yes, okay, one intensity measure might not be enough. There are several reasons. One main reason is that you might want to improve the precision by a vector EAM. For example, if you are developing fragility curves for a component that has two different failure modes, one low and one high frequency failure mode. In that case, you could improve your risk estimates by introducing this information in the analysis by considering the vector hazard and the vector fragility for two intensity measures. Then another case where it might be of interest is multi-hazard PSA, so probabilistic safety assessment. In that case, you might want to consider two correlated external aggressions, such as a tsunami after an earthquake, or also a seismic main and aftershock. So you have two events. You have the one intensity measure for the main shock and one intensity measure for the aftershock. And then another way to use, of course, the output of PSHA is not only to develop hazard curves and use them within the risk estimates, but the output of PSHA is also used for record selection and for defining design level, such as the uniform hazard spectrum, UHS. So the vector hazard can also be used to define target distributions of vector intensity measures for ground motion simulation or selection for a given return period. Because the vector analysis has also an impact on the way to define the return periods. First of all, also some literature. There were several studies in the past, but really few applications of vector hazard until to risk. I think one of the reasons was because it's not very easy to compute the vector hazard. It's not very convenient to compute the multidimensional multivariate hazard within the hazard integral. So there was a need for an efficient method to compute the vector hazard. Because indeed, yeah, the direct integration of the multivariate hazard is not feasible in, yeah, let's say, industrial applications where you have many sources. There was some previous work. I picked a few. For example, there was one work of Iovolino in 2010, where with a very simple approach, it was only applicable to 2 intensity measures, and it did not really account for all of the scenarios because it was directly conditioned on a given set of magnitude and distance. Then there was a more complete approach, which was proposed by Zero and co-workers also in 2010. It was based on the conditional rates, and it allowed to compute the multivariate hazard more conveniently by computing this as aggregations. However, I would say that this approach requires additional computations, which also can be quite costly. And in addition to that, it also introduces new approximations due to the discretization that you use when you compute those conditional probabilities. Oh, I lost. Ah, sorry, okay. Thank you. I lost the presentation on on the computer here. So, okay, there were different attempts to develop a more convenient approach to compute the multivariate hazard. However, they were not fully satisfactory, I would say. Then, within the Metis project, there was a new development by Jem and by Marco, which I call it here recent source-based approach. I think Marco will tell you more about this approach and give you more details. But roughly speaking, it is based on the development of the multivariate Gaussian distributions for each rupture using the correlation model, mean and standard deviation values of the ground motions, because you know the distribution. The ground motion models have the log normal or Gaussian distributions if you apply the log, and then use this to compute the rates of occurrence for each source and scale by the rate to obtain the MRD. So I think you will hear more about that. It is an intrusive approach, and yeah, it has been implemented in the OpenQuake engine, so you can use it in the OpenQuake engine. But I would say it remains a little bit computationally intensive. At least I was not able to do it on my computer, on my local computer. Which is why I will also propose another approach here, which is based on what is called the copula method. In fact, it takes advantage of the fact that it is generally assumed by seismologists and in seismic hazard analysis that the correlation coefficients are not depending on scenario and site parameters. So the correlation models, for example, the Baker model, do not depend on the scenarios. Which means that you can also introduce the correlation in the PSHA output instead of introducing it when developing the hazard. And this is what I will present here. So it's a new approach based on the copula to construct vector hazard curves. I will show the methodology and the verification for a very simple analytical test case, and then give a very short application to the Metis case study. And then I will show some very, very simple, unfortunately, today examples on how this could be used in the risk assessment framework to compute risk and also the impact on the return periods. So why use the copula approach? Again, you can develop the vector hazard without any assumption on probability loss. I mean, that's a property of the copula. can be used for any probability distribution because, of course, when you have the hazard curves, you don't know the probability distribution. They are not log normal or Gaussian, such as input parameters. They have any distribution, but the copular model, in fact, it can be constructed for any probability law, and it's based on rigorous mathematical framework. It requires only common output from classical PSHA, such as the scalar hazard curves and the correlation coefficients provided by models such as Baker and others. So you only need the scalar hazard curves, the correlation models. In the middle you can see the Baker model, and then you can construct the two-dimensional hazard. And I have only one slide with some, let's say, mathematical details and some equations, because it's really quite easy to compute and to understand. So what we want to obtain is the multivariate cumulative density function, F. This is defined by the copula, and the copula is constructed only by the marginal density functions. So the marginal density functions are the F1 to Fk, and they are directly obtained from the hazard curves by taking 1 minus the hazard curves to obtain the cumulative density function. Together with the correlation coefficient rho and by using the multivariate Gaussian distribution. So this simple copula is based on the multivariate Gaussian distribution, but it's not a Gaussian, the copula itself is not a Gaussian distribution because it's obtained by transformation of variables, so to end up in a Gaussian framework and then construct this model. So it's really quite easy to develop. And it's possible, again, because the correlation coefficient does not depend on the scenarios MD, and also the correlation coefficients are invariant to monotone transformations, such as you use here, because you transform the probability distribution several times. And yeah, you can represent any probability distribution without any further approximation. Let me show you a first analytical example. So this is fully analytical. It was only done to check whether the approach could provide good results. So on the left-hand side, you see the two hazard curves. It's a simple case, a two-dimensional case. You have hazard curve 1, hazard curve 2. Here it's analytical. I did not use any PSHA. I developed some simple log normal model just to check. Then I added a correlation coefficient and I computed the two-dimensional density based on the copula model. And then here, of course, it was very easy to check the correctness of the model, because one very simple check is to check the marginals. So based on the two-dimensional model, I recomputed the marginals, the PDFs and also the CDFs. So here what you see on the right-hand side are the comparison of the initial marginals from the scalar inputs and the marginals computed from the two-dimensional model. So it fits very well. And here just another illustration to get a little bit an idea on what it does on the two-dimensional hazard. On the left-hand side, you have the case where you have no correlation, so you have two scalar hazards and you combine it to the 2D case without correlation of the two. In the middle you have moderate correlation, so close to 0.5, and on the right hand side you have a closely correlated case, so you have two intensity measures which are closely correlated, and you can see, so here it's the same scalar hazard curve, so you can see the impact it has on the hazard. Also, a last check here with this analytical model, because there was also the correlation. I showed you the verification of the marginals by comparing the marginals computed from the 2D model to the input, to the target marginals. Then there was also the correlation. For the correlation, it was here quite easy and convenient to simulate realizations of the two-dimensional model, because since I constructed this copular model, I can very easily simulate samples, 2D samples of the intensity measures based on this model. So this is what I did here. And then I simply computed the correlation coefficient to check the statistics. And I also computed, of course, mean standard deviation. And so the goal was to check that everything works fine. And it was the case. And on the right-hand side, you can see also the comparison of the theoretical model to the empirical model from the simulated sample. So that was only to check on a very simple case whether everything works fine. It's a verification. Now I will show you a very simple application, if I can call it application. It's really also some test case only to the Metis case study. I use the occasion to present you also the Metis case study. So in the Metis project, we have defined a case study with the goal to test all new developments based on this common example. The case study is a central Italian site. You can see it on the figure above there. It's in the region of close to Tuscany. And you can see here a figure that had been used to develop the hazard model. Where is it? Okay. So how?
The upper bottom, it should be this one.
Okay.
So, okay.
Thanks. It works. So yeah, the site, it worked. The site is here. It's close to Tuscany, and here you can see one illustration that has been used to develop the hazard model. You can see also the more or less exact location of the Metis case study. And of course, there is no nuclear power plant located in Italy at that site. And besides, also, it's in general difficult to find a real site for test studies or verification of new methods, which is why we developed a hybrid test case. It's based on data and information on this site in Italy that we obtained for the hazard and also for the site data, and a nuclear power plant and a fictitious nuclear power plant. I put here fictitious because it's not in Italy, but it's a real nuclear power plant. We obtained information by our colleagues in Metis project from the Ukraine. So we have developed models for the Zaporizhzhia nuclear power plant, which today has become a little bit famous for other reasons than seismic, unfortunately. But so we are studying this model onto this site. And here, just for information, you can see the uniform hazard spectra that are corresponding to the site for 1,000, 10,000, and 20,000 years. So this model is developed in OpenQuake. So here, now I use the results of OpenQuake, so the model from OpenQuake. And this is one example of two scalar hazard curves. I used here one case with some moderate correlation, so you have 50 hertz, if I'm not wrong, and you have 0.5 seconds and 0.05 seconds. The correlation for these two intensity measures is 0.67. So again, you can construct here the two-dimensional model, and here you can check by computing the marginals that they correspond to the input from the hazard model. So the input from the hazard model is here the derivative of the cumulative density function derived from the hazard curve. So that worked, at this point it worked quite well. But then the question, what can we do with it? Is it useful in practice to construct the vector hazard? Let me start by saying if there was very low correlation between the intensity measures, of course, it's not useful because you can compute the scalar hazard and you do not need to account for the correlation, of course. You can directly use the scalar hazard. If the intensity measures are highly correlated, it might make sense for hazard, but it does not make sense for structures because if the two intensity measures are highly correlated, it means that it's sufficient to use one of the intensity measures to have the whole picture. So for example, that's one thing I looked at. If you consider PGA, it's here the thick and blue line, it is very highly correlated to any other spectral acceleration up to 5 Hertz. So in this range, it's not very useful. The correlation coefficient is close to 1. But it can be useful in other cases where you have a correlation in between the two. And also, perhaps what is more prospective, it allows to consider cases where you need to consider combined failure modes. So you might have one equipment that might have 2 different failure modes, which might be sensitive to different intensity measures. And also, the combined hazards. If you want to plug this into the risk assessment, you need to, I don't need the pointer because I put it here, you need to add the information about the fragility. So the risk, a very simple case, is computed as the integral between the fragility curve and the hazard, which is obtained as the derivative of the CDF of the hazard curve. Yes, and here, this is the fragility curve. In the 2D case, I stayed with the 2D case because it's easier. You have the same thing, but now the fragility and also the hazard depends on the 2 variables. So you have again the 2D hazard as you have seen before with 2 intensity measures, but now you also need to compute the fragility for the 2 intensity measures. Of course, I show you a simple example here. Of course, reality is much more complex. There is not only one equipment, and the integral is not only such a simple expression. You have thousands of equipments and several failure modes, for example, in the nuclear installation. So the problem is quite more complex. But let's start with a very simple case to look whether there can be some benefit of this. I constructed a simple case for the combined hazard of main and aftershock here. You have 2 correlated intensity measures. The first intensity measure is, let's say, the PGA for the main shock, and the second intensity measure would be the PGA for the aftershock. And then, of course, the structure is likely to be damaged after the main shock. And the aftershock fragility depends on the main shock. So what I considered here is very simple. I considered that for the main shock there was no failure of the equipment, so no failure. And then I computed the failure probability given that there was the second aspect, so the aftershock. And I considered here to just test a very simple link between the fragility after the main shock, before and after the main shock. So I considered that after the main shock, depending on the intensity of the main shock, the component is weaker and is a little bit damaged. So this is what you can see here. You have the fragilities for the different main shock levels. So the capacity goes down and uncertainty goes up. And so here is the result for this case. You see a difference between the case where you consider the correlated main shock aftershock sequence by considering the correlation between the main shock and the aftershock hazard, and the same calculation where you do not consider this correlation. You do not account for the correlation between the main and the aftershocks. It's just to highlight the impact for a simple case. This is another very simple case, and even it was not for the Metis case study. It's really only an illustration where you can have the bivariate hazard curve. It's the blue curve here, and then you have the two-dimensional fragility curve. This case here could model a case where you have two correlated intensity measures and one equipment with two failure modes. So the structural capacities are moderately correlated, and you have OR conditions. The component fails if one or the other failure mode is activated. Of course, here don't look on the numbers. On the other case, it was for the Metis case study. Here, the numbers are. In fact, I computed this for the analytical test case where I had the log normal hazard curves. But you can see the difference between considering only one failure mode for the first failure mode, only one failure mode for the second failure mode, then combining the two failure modes, but not using the vector hazard. And then here, combining the two failure modes together with the correlation of the hazard and the vector hazard. So this is ongoing work. We would like to try to do some more complex applications to make this case study, and also, of course, to the nuclear power plant model that we have for some more realistic test cases. I have another point about the return periods, because the vector assessment also has an impact. It also illustrates some impact on the return periods, because when you consider two intensity measures, you can consider different cases. You can consider the case where you want to have simultaneous exceedance. So this is what we do in the uniform hazard spectrum. We consider the cases where you have simultaneous exceedance of the thresholds for the same return period for all intensity measures that you consider. On the other hand, something which is much less strict, it would mean that you have arbitrary exceedance. So you have exceedance if you have exceedance for only one of the intensity measures. And that has a quite big impact on the return period, because, of course, the return period for arbitrary exceedance is much less than for simultaneous exceedance. And in particular here, this is also, I found it quite interesting, this illustration, to consider multivariate return periods. Here you have, again, only two intensity measures, so two variables. If you consider the case where you have, here this is the base case. You have one intensity measures, and each time you say, okay, I consider the case with 10,000 years return period. Here, now you have the case where you have two intensity measures, and you consider them together. And you consider the probability of exceedance of the threshold of the 10,000 years threshold, for example, for both of them at the same time. It means that if you do not consider correlation, of course, the return period of the combined exceedance is 100,000 years, because it's one times the other. It's not correlated, and it's simultaneous. While if you consider the correlation, here you have very strong correlation. Of course, the simultaneous return period is the closest one to the scalar return period, because if one exceeds, it's very likely that the other also exceeds. While if you have moderate correlation, it's something in between. Then here the comparison to arbitrary exceedance, where, of course, the return period is much less, because it's much more likely that one or the other exceeds and not both together. And the last line I put it here, it's also one work that we want to do, is to look on the definition of multivariate return periods. In the literature, you can find some work onto that. Because at the end, if you look on the uniform hazard spectrum, I think I put it here. Indeed, the return period of the uniform hazard spectrum is much higher than 10,000 years. Each point on the uniform hazard spectrum has a return period of 10,000 years. So it would be interesting to compute here already the real return period of this uniform hazard spectrum, because that's the the design level that we consider if we choose ground motion that is in agreement with this uniform hazard spectrum. And then also it can allow to define strategies for record selection, perhaps similar to what is done in the CS approach, where you do not have simultaneous exceedance for all levels at one time, but you have exceedance for one intensity for one of the intensity measures, but not for all at once, which would lead to really 10,000 years return period and not a much higher return period than what is here. Okay, that's all that I wanted to show. Yes, the copula approach that I showed, a summary, it can be obtained only by post-processing of classical PSHA outputs, such as provided by OpenQuake. You can obtain an exact representation of the marginal, as I tested, and there was no supplementary hypothesis in addition to those already accepted, such as the Spearman's correlation coefficients for the different intensity measures. And it will be available, it's not yet available, but if you want to test it, it will be available on the Metis GitLab, which is available to the public. Then the implementation of vector risk assessment. As you have seen, there was still some work left to finalize this and to really assess the impact and the interest of these approaches, because indeed it impacts the full analysis chain, hazard, fragility, and also system and risk, because of course if you consider a real system, you have more than one equipment and it might get computationally very, very demanding. And yeah, it would be necessary to implement this in the SPR framework and check benefit versus supplementary effort to compute vector fragility, hazard, and also the failure trees. I use also the occasion to give you perhaps a quick overview of the Metis project, because this workshop here has been organized by Marco in the framework of the Metis project. In the Metis project, we have the goal to improve the state of the art in seismic risk assessment on the whole analysis chain, from hazard to risk quantification. So we have 4 main work packages. The first one is about seismic hazard, and we adopted a strategy to develop seismic hazard on rock, or rather bedrock. And then, in the second step, develop ground motion and site response only for the scenarios that we are interested in, and only for the cases where we want to carry out structural analysis. So the hazard itself is at bedrock level. And yeah, then we also have a work package about SSCs, so structures, systems, and components, response and fragility, and risk quantification. So the goal is to try to improve state of the art and practice in the nuclear, and also to disseminate it to engineering. This is why I think the Metis case study is very important, because it allows to assess the feasibility and the cost benefit of new and improved approaches within the project. And at the end, we hope that we will end up with some recommendations and experience feedback in a final handbook based on all the development in the project. And yeah, of course, compare always new methods to current practice, because if we want people to adopt the new approaches, we need to show that they are in a certain way better or more efficient than existing approaches. Also, in the Metis project, I like to point on this is the open source philosophy. So we try as much as possible to work with open source codes and also disseminate everything that we develop as open source tools. I think it's beneficial for everybody. It can optimize, of course, uptake and dissemination, and also acceptance by the community and regulators, which is important for us, of course. Yes, and which is why, so in the Metis case study, in Metis project, we are working with Marco and OpenQuake, so all the developments related to hazard are done linked to OpenQuake and can be made available to any interested user. Okay, so thank you very much.
Thanks, Irmela. Questions? Comments?
So currently when we run vector hazard in practice, it's almost always the indirect method, so because it's easy to do. How much does, I see the math is cleaner in what you're doing, but how much does it actually change the results? Do you have any comparisons of just running the indirect method compared to the cupola method?
You mean in terms of computational time? Or?
No, results of the vector hazard calculation. Is it changing? Is it mainly a computational efficiency, or is it actually getting you different answers?
I think my main motivation was to make something quicker to compute than what is there. I don't think that it's more precise than the method from OpenQuake. I don't know if you want.
That's my very personal point of view. I think that you might see differences when you have ground motion models with a lot of explanatory variables, because in the indirect method, unless you have a very articulated way to create a disaggregation that takes into account all the explanatory variables, okay? So if you don't have that, you need to take assumptions of a number of parameters, right, other than magnitude and distance. So whereas in this case, you don't have to take that approximation. And depending on the structure of the hazard model that you are using, there might be cases in which the differences might be non-negligible, let's say. But so far, we didn't really explore the spectrum of cases where this might become clear. But certainly is something that we would like to do. And we are in a sort of similar situation with the calculation of the conditional spectrum, because as I was telling you yesterday, and I will briefly mention in my presentation, so we put in the OpenQuake engine the methodology that is calculating the conditional spectrum, not the conditional mean spectrum. So we are able to really take into account all the scenarios that are admitted in the PSHA model, all the realizations of the logic tree, and calculate the conditional spectrum according to that. So, and if you instead calculate with the conditional mean spectrum, also in that case, there might be cases, okay, not always, okay, in which we might see some differences, and that's also partly described in the paper of Lee and Jack Baker, where they explain that, for example, for the standard deviation, you might see some differences between the two approaches. The extent to which this is then relevant on the engineering side, I'm not in a position to evaluate that, sorry. It's too far from.
Thank you, Irmela. This question may show more my ignorance than anything else, but the correlations that you are working with are correlations of ground motions. Can you always assume that the same correlations are preserved for the hazard?
To my opinion, and if I look on the equations, as long as they do not depend on the scenarios, yes.
I have, thanks for your presentation, and I have a curiosity about the correlation. The method you used is Spear's-Mann correlation coefficient, and there are also like Pearson correlation efficient. So I'm wondering why you apply this for this correlation. Yeah, I'm wondering why.
The difference between the two is that the one is based on ordered statistics, so it's not it only looks on the orders and not on the values, so it's a more general one, and this is why it's more convenient to use it.
Okay, can I ask one more question? You considered the cross correlation of ground motions, and I'm wondering if you also considering the spatial correlation of ground motions. Like there are some models has already published and also has some influence for the risk analysis or something. Yes, so I'm wondering.
Yes, here in this work we did not consider spatial correlation, but of course in the risk computations there was also there was another. I mean, it's another topic of study. You mean the impact of spatial correlations if we consider several structures? Or
Yeah.
you mean? I mean, here we did not consider spatial correlation. We only considered correlation between intensity measures.
Yeah, I got the point. Thank you.
So you mentioned that this is motivated by computational speed, but is it actually faster? I mean, is it faster because you're trying to compute the joint CDF when you don't need to actually do that?
It's quite fast with Python, and it can be even much faster because it looks like Python is not, the Python modules are not optimized, but I mean, I could compute all this on my computer while the...
But I guess I'm saying if you...
Okay, I could not compute anything else, and all the other approaches cannot compute them without the...
But so so as soon as you go to more than a couple of IMs, then the computation of the joint CDF is for each scenario is intensive. But for the risk, you have to differentiate that back down to rates anyway. So for risk, you only ever need the mean rate density, which you can stack from the joint PDFs without doing any integrations. So why can't you just, for each rupture scenario, stay on the densities, stack them proportional to the rates, then you get the total joint rate density for all rupture scenarios. And then if you want to construct your joint CDF from that, you can. But if you want to stay for risk applications, you can just then consider each rate combination without ever computing the CDFs. So when I do it, the computational difference is trivial because you're never actually doing the integrations. And there are ways if you're doing it, if you're going to do 2 IMs anyway and you're storing those rupture scenarios, the the correlation matrix is fixed and you already have all the moments for the different IMs. So you can just take your lists of the moments for each rupture scenario with their weights and join them together afterwards. So I think there's some, yeah. But then, so is it fast? So if you do it that way, is it faster using copulars? Okay.
What Irmela does is faster, but of course there's a strong assumption on the correlation structure that right now is rather simple, right? So in a perspective, maybe we might think that the correlation structures might become a little bit more articulated, and in that case, a coupler approach is clearly a bit more difficult to apply. Whereas what you are saying, which is something along the lines of what I'm going to describe in my presentation, is still giving you the possibility of taking into account more complex correlation structures. But I cannot quantify in terms of Irmela's computer units the computation demand.
Yourself. So we got already a flavor. So next presentation is Marco, thanks Irmela, and he's going to discuss new OpenQuake features developed within the Metis project.
Okay, good morning and thank you. So in my presentation, sorry. In my presentation, I'm going to give you an outline of the improvements that we made to the OpenQuake engine within the Metis project. And I must say that I'm very grateful to Irmela for involving us, because it's very difficult in our work, in a day-by-day work, to find the time to have substantial improvements to the OpenQuake engine. So in this project, we had the possibility of really adding a number of things that otherwise would have been very difficult to add. So here you see a number of persons that are working together with me at the GEM Foundation, but as Irmela said, a lot of work that we've been doing within Metis was really a collaboration between different organizations. So I want to acknowledge, of course, the contribution and a lot of discussions that I had with Irmela, but also with Paolo and Nevena from youth, because this was, in many parts of my presentation, there are contributions or ideas that came up during discussions with them. This is the outline of my presentation, and as you can see, unfortunately, I was not very creative. It's a sort of shopping list, but I hope that in the shopping list you will find something interesting in what I'm going to explain to you. So the work that we've been doing essentially is subdivided into free tasks or free topics, as you will, or free areas in which we've been trying to add to the OpenQuake engine new capabilities or to find new methods that could work efficiently inside the OpenQuake engine. So the first one is the propagation of epistemic uncertainty, so find more efficient ways to propagate epistemic uncertainties. The second one was work on improving the capabilities of, or more efficiently computing the capabilities of vector-valued PSHA and the conditional spectrum. And the last point that I will only briefly touch in my presentation is about the modeling of earthquake sequences taking into account aftershocks. So in other words, how to calculate PSHA, also taking into account the contributions of aftershocks. So starting from the last point, as I said, because I have not much to say, this is work mostly done by Richard Styron, and I give credit to him for almost all the work that is done here. But the idea that we developed in this case was, to start from a traditional main shock-based seismic hazard model. And we developed a methodology that is able to basically bring back what we are usually taking out when we are developing the model with the clustering. And so we developed a methodology that, starting from the main shock-based hazard model, is looking at the different ruptures. For every rupture, is creating all the set, is finding all the set of ruptures that could be, let's say, representing an aftershock for that rupture. And through this process, what we do is to modify the magnitude frequency distribution of every source to take into account that part. So we end up having essentially a new hazard model with a modified magnitude frequency distribution, and with that model we are able to calculate a hazard that is also taking into account the aftershock part. If we move to the vector-valued PSHA and the conditional spectrum approaches instead, the work here, as I said, was subdivided in these two topics. And on the conditional spectrum, what we did was something very, very simple. So what we did was to look into the literature. There's a very good paper from Lin et al. Published on BSSA in 2014. We took the most complex and articulated methodology, because that was indeed the one that we thought was the most appropriate one for our needs, and we implemented that one inside the OpenQuake engine. So it's actually implemented as a post-processing tool, so initially the engine is calculating a traditional PSHA analysis, and with the information that is stored in a second phase, we are calculating the conditional spectrum. This is a feature that is already available in the OpenQuake engine. Of course, I don't pretend that you take note of that. I am planning to share the slides, but this is just to say that if you are willing to test it, it's already there, and there are examples that you can use. If we move instead to the vector-valued PSHA, so initially what we did again was to look into the literature, and of course we started from the work of Bazur and Cornell 2002. As Irmela explained very clearly, that is the reference methodology, the so-called direct method. And so we developed an initial version of that methodology that was for a simple hazard model without epistemic uncertainties, and we immediately discovered that was very computationally intensive. Also my laptop, not just the one of Irmela. And then at that point, of course, we started to consider alternative approaches. And we started to look at the methodology proposed again by Paolo Bazur et al. In 2010. That is called indirect method, because that methodology is indeed using disaggregation to store, let's say, contributions of various combinations of some explanatory variables, okay, to the combination of intensity measure types that you are using to calculate the vector PSHA. But as we were discussing before, that methodology, of course, is very interesting and is certainly far more efficient than the direct approach method. But it has also, to a certain extent, the limitation that when you are using gram motion models with a large number of explanatory variables, unless you are able to create a huge matrix that is able to take into account all those variables, you need inevitably to take some assumptions of some of them. And so we wanted to, let's say, try to find an alternative approach that is overcoming this limitation. So what we end up with is an approach that is using the same concept of the disaggregation matrix, but in this case, rather than using a disaggregation matrix that is in terms of magnitude and distance, we're using, for the case of two intensity measure types, a matrix that is 4-dimensional, in which we have the mean of the logarithm of gram motion for the two intensity measure types and the corresponding total standard deviations. And why we do that? Because if you look at this plot, if you look at this plot here, this is a plot that is in a very, very schematic way and trying to summarize what is currently done when you use the direct approach for calculating vector value PSHA. So when you calculate the direct approach, in your hazard model, you take all the ruptures. For every rupture, you calculate the two values of the mean of the logarithm of the gram motion and the corresponding standard deviation. You take your correlation model and you create a multivariate Gaussian distribution with which you can create then the mean rate density distribution. And you keep repeating that for every rupture that is part of your model. Doing that is quite computational demanding because creating the multivariate Gaussian is, particularly in Python, not very efficient. So what we decided to do was to explore the possibility of storing in this 4-dimensional matrix the rates of occurrence of the various ruptures for combinations of the two logarithms of gram motion and the corresponding standard deviation. And if we do that, and in a second post-processing phase, for every discrete combination of the two values of gram motion and the two values of the standard deviation, you calculate the multivariate Gaussian, and then you calculate the mean rate density, you are able to perform, for example, calculations for models with a discrete number of realizations of the logit tree. And that's something that for a direct method we haven't been able to do so far. The model, according to the tests that we've been doing, is working reasonably well. This is for a toy, a simple toy model. I think in this case I was using a fault. And here you have a comparison on the left between the mean rate density calculated. So the colors are showing the mean rate density that is calculated using the direct method. And with this dash orange isolines, you see instead the mean rate density that is calculated using this approach that I was explaining. And on the right instead, you can see a comparison between the marginal distribution that you obtain from the mean rate density using the direct method and the original hazard curves. And let me use again the pointer, So this one is, showing correctly on, there you go. So this one is the comparison between the hazard curves and what we get by marginalizing the mean rate density using the direct method. And this is what you get instead using the indirect method. So in both cases, as you can see, the match is quite good. We've been also doing some tests for the Metis test site that Irmela was describing before. And here, despite overall the methodology seems to work again still reasonably well, you see that in some cases, in some parts, and again, So for example, in this part, if you look at the comparison between the original curve giving you the rate of occurrence of a certain value of ground motion and what you get by marginalizing the mean rate density, the match is not perfect. And same, you can see some differences here. We are attributing these differences to the binning that we are using to describe this four-dimensional matrix. And so what we are doing right now is to work to ways to automatize the definition of these bins in order to minimize the differences that you see here in this comparison. So this methodology is also implemented in case you're willing to test it, and here is just a link to an example available inside the OpenQuake repository. Last part of the presentation is on the propagation of epistemic uncertainty. And so in this case, our goal was to explore the possibility of finding more efficient ways of combining or processing basically the logic trees. And as a first attempt, what we did was to basically expand capabilities that were already in the OpenQuake engine. So we added the possibility of applying the weights at different stages of the processing of the logic tree, and we also added the capability of using Latin hypercube sampling instead of the traditional Monte Carlo sampling approach. But in the second part of the work that we've been doing inside this activity, we started to develop an approach that is propagating epistemic uncertainty that is hopefully a bit more efficient, but also, let's say, that is giving us more flexibility in structuring the logic trees and the other models more in general, which is something for us very important, not just for the Metis project, for example, but also for the big collection of models that we have at GEM, that is a so-called mosaic that has a global coverage and includes a lot of national seismic hazard models that are also, of course, very important for assessing hazard. So, oh wow, that's no. Okay, I will explain it, sorry. I didn't get until this point in checking the presentation. So disappointing. Okay, so how do we organize our work for this? So what we decided to do is to, first of all, split the hazard model into a number of, let's say, sub-models, each one for one individual source. So we have, for a source, the corresponding structure of the logic tree. And if you do that, clearly, when you want to explore the full spectrum of the epistemic uncertainties admitted by the combination of all the sources that are contributing to the hazard at one side, what you do is to combine the realizations of the different branches of the individual source logic tree. Let's see if also the following ones will be. So, and there are cases, of course, when you do that, in which the single source logic trees are, let's say, totally independent, or there are cases in which these individual source logic tree can share some uncertainties. For example, if you have two sources that are part of the same tectonic region, there might be cases in which you might want to use the same ground motion model logic tree for both of them. So in that case, you are clearly introducing a correlation between the logic trees of those two individual sources. Oh shoot, this is also. So and when we process, as I explained, the logic tree, okay. What you end up having is a set of seismic hazard curves that you see here, and each hazard curve clearly is defining a set of annual frequencies of exceedance with the same cardinality of the intensity measure levels for which you are defining that annual frequency of exceedance. So the final hazard curve at your site will be the sum. So if you take one realization, okay, the one hazard curve for one final realization will be the sum of the hazard curve that you calculate for a certain realization for one source logic tree and another hazard curve for another individual source logic tree. Okay. So now I'm going to explain the way in which we are structuring our problem. And so here you in this plot. Oh, sorry, I moved. In this plot, you see what is the output of individual source logic tree. So for each intensity measure level, if you take all the realizations of the different hazard curves, you will have a number of values of the annual frequency of exceedance. And with that information, what you can construct is a discrete histogram. And this discrete histogram will represent a probability mass function by definition, because the set of the weights assigned to all the realizations, okay, for each intensity measure level sum up to 1. And therefore, the histogram by construction will be also directly a probability mass function. And we can repeat that for every individual source logic tree, okay? So we do that for each intensity measure level of each individual source logic tree. We can come up with this histogram that is describing the probability of having a certain annual frequency of exceedance. And since the total hazard is then the sum of this annual frequency of exceedance, the problem is essentially the sum of probability mass functions. And if you use what is regularly explained in basic probability theory textbooks, the sum of two probability mass functions or two probability distributions is simply the convolution of the two. So with this methodology, so if we instead of then processing the logic tree, we use this convolution approach. We are able to obtain as a final result for each intensity measure level a discrete probability mass function that is giving you a description of the probability of having a certain annual frequency of exceedance. And using for each intensity measure level that distribution, you are able to calculate all the statistics that are usually used for representing the hazard, such as mean hazard or median or percentiles. Of course, you are completely losing the connection between a value and a certain realization that you have when you are propagating all the possibilities. But rarely, at least in my experience, we've been doing that, and that's in any case something that can be done a posteriori if there's a specific need for a certain combination of realizations. Of course, there is the case, as I was explaining, in which there's a correlation between individual source logic trees. And what we do in that case, okay, in this case, it's not. So what we do in this case, so here in this plot, in this picture, what I'm showing you are two schematized logic trees. This is a very simple logic tree for a source A, and this is a second logic tree for source B. There's a first branching level with some uncertainties that I didn't define, and there's a second branching level in this case in which we are using 3 different gram motion models to represent the epistemic uncertainties in gram motion. And here I'm showing you basically the correlation between the realizations of this logic tree using the ASK 2014 gram motion model and the corresponding realizations in the other part of the logic tree. So with all of that, what we do is to create basically so we repeat what I'm showing you here, that come up with this combination of all the possible combinations of the realizations of the 2 logic trees, and we repeat that for all the options that are admitted by the logic tree. So we do this for the ASK 2014, we do this in the second case for Campbell and Bosonia, and then for the Chu and Young's. What we obtain in this case, okay, and what we can do again in this case is to repeat what I explained before. And what these 3 cases are representing, okay, each one of them, what is representing is an alternative distribution of the annual frequency of exceedance, okay, based on the type of gram motion model that you are using. And what we do in order to go back to the case that I was explaining before, in which we have independent representations, is to, in this case, calculate a mixture distribution of the 3 that are admitted by the 3 different groups. Once you do that, you go back, as I explained, to the previous case, and you are able again to apply the convolution between the independent groups and come up with a final description of the results. How this is working? Again, if you take a relatively simple case in which you have a couple of false sources and the gram motion characterization, that in this case you are assuming independent, despite you will see that the models I'm using are exactly the same. So here you have a first, this is a very schematized description of the logic tree with the type of epistemic uncertainty, the branches with the values. And same here, you have the same, but for the gram motion model component. And this is one source, this is another source, where again there is, we have uncertainties on, so we are defining a Gutenberg-Richter distribution starting from slip values with certain values of rigidity, 2 different magnitude scaling relationships, 2 different values of the lower seismogenic depth, and this is just an additional branch that we use in order to calculate the max according to the change that we are applying in the lower seismogenic depth. But using this toy model, we can, of course, perform comparisons between the, what we get using a traditional processing and what we get using the approach that I was describing in this case. Here I'm showing you a comparison between the results for the mean hazard curve and for the median hazard curve, and as you can see, the match is good. And the methodology is working conceptually in the same way also for magnitude. So you can perform the same thing that I've been explaining for the hazard curves for the different realizations of the disaggregation. And here I'm showing you a comparison still for a relatively simple hazard model where I'm comparing the values of the annual frequency of exceedance for the different magnitude bins in a disaggregation that is just on magnitude. And as you can see, the values are all very well aligned on this line, showing that basically the match between the results provided by this methodology and the traditional one is good. And again, just to show a comparison for other results, this is instead the result of the mean disaggregation for in terms of magnitude and distance. On the left, using the traditional approach; on the right, using this methodology based on convolution. And as you can see, we are, of course, identifying exactly the same model value. The probability in that case, or if an annual frequency of exceedance, is almost the same. And overall, the structure is almost coincident. How it works in terms of performance. So this is, again, a comparison based on a relatively simple model. And if we start actually from the plot that you see here at the bottom right, so just to mention that the results that we are considering are actually very, very close. Okay? But if you look in terms of execution time, clearly when you are using an approach in which you are applying sampling, the larger is the number of samples, the higher gets the time that it takes to perform the propagation. Whereas in our case, this is clearly independent on the number of samples, because once you have the histogram, you go. In terms of memory usage, again, in the case of a traditional approach, the memory consumption increases with the number of samples, whereas in our case, again, since we are not depending on samples, the memory consumption is very low and remains stable. And also in terms of so if you take, let's say, the right hazard curve, and then you perform ratios against what you get by doing Monte Carlo sampling or using our approach, you can see that in our case we are getting a very good match, whereas of course in the case of sampling that is improving with the increase of the number of samples. But overall the method seems to be relatively precise, at least until, let's say, relatively small annual frequencies of exceedance, then it gets a little bit more unstable. So that's concluding my presentation. I don't have many conclusions, so hopefully I gave you an overview of what we've been doing, and I hope I've been sufficiently clear despite the figures that were turned up. Of course, these are all new methods, and they will require a validation that goes beyond what I've been explaining here. And there are new things that most probably will need to implement in order to make these methods usable with more confidence by the general users. But overall, according to the tests that we did so far, they seem to be promising. Okay, thank you.
We have time for questions. Just for your peace of mind on the laptop, we're okay.
Thank you, Marco, for the presentation. I have a couple of questions about the uncertainty propagation. I imagine that when you, let's say, publish these new methods, there will be an option to choose which one to use.
Yes.
For example, sample, what in Monte Carlo, what in Hypercube, and the new one, the convolution one. Do you have, let's say, a time frame? When do you expect to make this available?
So the time frame was actually scheduling a sort of initial release by the end of this year, but I'm not sure I will be able to do that. Or maybe let me articulate it a bit more. The methodology that I explained for the uncertainty propagation is all implemented. It's not yet in the OpenQuake engine because so far it has been tested only for one site because, of course, in Metis we had the goal of working on site-specific hazard. But the methodology is actually, in my opinion, particularly promising for national hazard studies because my hope is that with this methodology we will finally be able to incorporate say, a proper structure of epistemic uncertainties in the national seismic hazard models and not just in the site-specific ones. And secondly, if it's working well, at GEM I think that we would like to probably structure also the hazard model in a slightly different way. So right now you have a very huge, a very bulky model. So if you take the regional ones that we have, the European hazard model, where there is everything. But if this is going to be, let's say, efficient and successful, what we aim to have is a collection of individual source hazard models that combined, okay, in terms of results, are giving you the hazard at a certain point. That it will be a much more modular structure of the models, and will give you the possibility to more easily, for example, update a certain component if you can assume that, of course, the sources are totally independent one each other. But if you have, I don't know, a full system, you can think about changing the full system and maybe the source that is taking into account the distributed seismicity part around the full system without the need of changing the entire model and rerunning the entire model, because what you will need to do is to rerun what is the contribution, okay, the hazard that coming from that source, and you recombine.
Yeah, and that's actually very good to have the individual logic trees of each sources, because the current way, I mean, it's done in OpenQuake, but not only in OpenQuake. It's complicated. It becomes very complicated to incorporate differences in or updates in a single. Okay, maybe for a single source logic tree not, but if you have multiple sources to do it at the same time, it's quite complicated. Okay, thank you.
Other questions? We have time.
You talked about the correlation in the ground motion models on your logic trees,
Okay.
right? But the source models get more complicated as well with some correlations between sources. Is that, usually that's why Monte Carlo sampling is used, because it's really easy to build in complicated correlation structure, but can you accommodate a additional correlation between the source models in an easy way?
Yes, so conceptually it wouldn't change. What you need to do, okay, when you have correlations is to create the group that is including all the sources that are sharing a set of correlations. It doesn't need to be just one, but it can be a set of correlations, part of them in the source model and part of them in the ground motion model. And once you have that, you need to follow that process of finding all the combinations that are sharing the same set of variables, okay, that are correlated, create that mixture model that is described, so mixture distribution, And from that point on, you have a new component that can be considered independent from all the others and can be convoluted. Yeah, but conceptually, what I showed for the ground motion model works exactly in the same way for a correlation that instead is on the seismic source characterization rather than ground motion characterization. It doesn't change.
And that's not a difficult thing that, or the way you have it set up, you can handle a really complicated correlation structure?
What at the moment I would say that I wouldn't have a clear idea, okay, of how to account that is when there's a partial correlation.
Right.
Okay. When there's a partial correlation, maybe the methodology cannot be modified in a way to take that into account. But
what I think you also can take advantage of this is when we build a logic tree, often we'll have an underlying distribution and you'll take 3 points to describe that or 5 points.
Yeah.
And if you're going to do your convolution, you could actually be trying to replace that with the full distribution.
Yes. Yeah, you don't need.
That will be a much,
Yeah.
a big improvement as opposed to these tiny logic tree nodes with 3 branches is not a good way to represent the full distribution.
Yeah.
Yeah.
You're absolutely right, Norm. So in this case, we don't have limitations in terms of the number of branches. And you can actually start, as you said, directly from a distribution.
Put the whole distribution in, yeah.
More questions?
I have a
Comments?
question for Peter, if no one else has a question. Is what I explained what you were saying before, Peter? For the vector part. Okay. Okay, cool. Maybe.
I mean, yeah, lots of similarities and conceptually, but some differences. It's pretty easy just to show you some code or something.
Okay. Okay.
For this, now I've got the microphone. So the correlations you talked about, you're saying, identify a correlation in ground motion or a correlation in source stuff, but you're going to have multiple correlations. So how are you tracking the groups? Is it looking for minimal sets, like the smallest correlation structure in the tree, or how do you? So, for example, imagine you have a source model and you use the same source scaling relationships for all sources. Does that mean that your group is the whole tree?
Oh, in that case, clearly, it's possible that you will lose efficiency but in what I was explaining, there is also, when you are processing the groups, the possibility of using internally convolution that I didn't explain that might make things a bit more efficient also in that case.
Yeah, so you could have basically subgroups, look for minimal sets, convolve to get high-level sets, and then, so basically a tree of convolutions, so you're identifying this minimal correlation structure. Yeah.
But that's a good point, and there will be for sure other cases. For example, I had a couple of meetings because I shared an initial version of the tool that with colleagues working in Slovenia, and they also had good points that when I was developing the methodology I did not consider, and I'm sure that there will be many more. So your one was also a very good one. Yeah.
Thank you, Marco. You were quite sharp in describing the implementation you did on main and aftershock hazard. Can you say something more, or can you just have an idea of when these new functionalities will be available?
It's already partly in the OpenQuake engine, and actually Michele, the lead architect of the OpenQuake engine, was indeed adding a new pull request that is cleaning up the code that Richard wrote So it's already inside the OpenQuake engine. And well, the methodology in itself is interesting because clearly it's starting from a traditional model. You don't need to start from scratch. But of course, has also limitations because if you are willing to, for example, do an incremental risk analysis with this approach, you are not able to do that. So you are not able to take into account the damage generated by the main shock and then the damage for the following aftershocks because you lose that in the model. But it's a relatively efficient way to instead have a look and see what the ground motion, the hazard can be when you are bringing back the contributions from aftershocks. The work that we did, especially at the beginning when Thomas was working with us, because in Metis we also had, we've been doing work on the clustering. So Thomas developed a methodology that is studying the extent to which the catalog that you are obtaining after the declustering can be considered Poissonian in space and time. And so when we were working with Thomas, we were trying to make sure that the structure used to the cluster was also the same one that we were reapplying a posteriori when we were repopulating the model in order to be fully consistent. And that's probably still one of the points that requires some work because clearly you need to make sure that you do the things consistently. Otherwise, you end up having Mach-2 frequency distributions that are completely invented if you are not consistent with the two steps of the process.
Okay, we have 2 minutes for another question, otherwise coffee time. If there aren't any more questions.
Okay, we are ready
Thanks,
for coffee.
Marco. Yes.
Thank you.
Is my presentation there? That's what I would I wanted to check.
Yes, I need you to be more loud. Call everyone. They are coming. Okay, we can start. Next presentation is by Nevena Šipčić and Pablo Inarritu, and the title is Uncertainty in Fragility and Response Hazard Curves Due to Ground Motion Record Selection.
Thank you. Good pronunciation. So, hi everyone. My name is Nevena Šipčić and I'm Mike, right? Thank you. Okay, perfect. Thanks. So my name is Nevena and I'm a PhD at USS Pavia. I'm finishing this year and I'm working with Paolo Bazzuro, he's my supervisor, and Pablo, my colleague here, who will also present, is also his student. So today we are going to talk a little bit about the uncertainty in fragility and response hazard curves. It's kind of a change of the topic because we talked about the hazard mostly so far, so this will be a little bit different. The work that we are going to show is not only the work of me and Pablo, but also of our supervisor Paolo and our colleague Mohsen Korengi. So the presentation will be in two parts. The first part I will present, and it will be more theoretical, and I believe for a lot of you kind of basic, let's say, just a little bit about the record selection and about deriving the fragility curves. So that we can set the scene for the second part of the presentation, which is more practical and some studies that we actually did and conclusions that we made, and that's the part that Pablo is going to show you. So I will start from the performance-based earthquake engineering. Basically, when we think about performance-based earthquake engineering, in most cases we think about a spear integral. So I will just explain conceptually and briefly what do we do here. Basically, we want to find the rate of exceeding a certain decision variable, which can be anything that the stakeholder is interested in, from the fatalities, money, repair time, or more recently, sustainability metrics. And we have four parts of this integral. The first part is hazard, which in this case, for this presentation, I'm assuming is scalar. So basically, we are finding the rate of exceeding a certain intensity measure, which can be PGA, SAT1, or whatever we are interested in. And then the second part is the response analysis, which is the distribution of an EDP given the intensity measure. This EDP can be drift, peak flow acceleration, dissipated energy, or something like that. Then the engineering evaluation, which is the distribution of the damage measure, which is usually discretized in damage state, given the EDP. When we have these two steps together, we get something that is called fragility curve, which is the probability of exceeding a certain damage state given the level of ground motion shaking. And then we can go to the last part, which is the loss analysis, which is calculating the losses given this damage measure. So if we make a link between the fragility part and the hazard curve, we can get something that is called the response or the demand curve. And I'm mentioning this here because later we'll talk about it briefly. So in order to get today we are focusing on the fragility curves. And in order to get the fragility curves, we need to select the ground motions. So how are usually fragility functions derived? In an ideal world, we would derive them empirically, but unfortunately, usually we don't have enough data. So what we do is we derive them analytically. There are different ways to do this. I will mention here just two. One is the incremental dynamic analysis, which is like a dynamic pushover. So basically, we take a single set of records and we scale them incrementally, and we run them on our structure and get the response. What is important here that this selected sets of records is not hazard consistent. So it's kind of a in relative terms, arbitrary sets of records. Another approach is to use multiple stripe analysis, where we define different intensity levels. So for the different levels of ground motion shaking, we select different sets of ground motions, and we select the ground motions to be hazard consistent. And what I mean by hazard consistency is we select the sets of records that are expected to be the site of our interest. So in that way, we get something like this, which is multiple stripe analysis, and we are going to focus today on a multiple stripe analysis. Before I go to the fragility curves, I will just mention briefly why do we care about the hazard consistency. For example, I'm showing here the study done by Korangi et al. In 2017, where, well, fragility curves are usually, as I said, when we have the scalar hazard, then we have the fragility curves that are based on a single intensity measure, which can be SAT1, PGA, average SA, or something like that. And what is important to remember is that in most of the cases, intensity measures other than the conditioning intensity measure also affect fragility curves. So for example, if we have one building that we place at 3 different sites in Turkey in this case, which have different hazards, so it's the same building. If we run the analysis and if we get the fragility curves, we will have fragility curves that are different, even though we have the same building and the same level of ground motion shaking, okay? So why is this happening? It's happening because the intensity measure is not sufficient enough and because the IMs other than the conditioning IM do matter. So that to say that the way in which select the ground motions matter and hazard consistency is important. How can we select the records to be hazard consistent? I would say the state of the art is right now is to select the records so that they have the spectral shape that is expected at our site. So what I'm showing here, let's say we have a structure for which we believe that SAT1 is the most relevant ground motion to predict the response of that structure. So on the left, I'm showing the hazard curve in terms of the SAT1, and I'm here defining different levels of intensity. So that are these horizontal lines that you can see on the hazard curve. For every single intensity level, we can derive the conditional mean spectra in this case that I'm showing. So you, with this blue dashed line, this is the conditioning period, and every gray point on this line corresponds to the point on the hazard curve. The points other than the conditioning one we get them using the correlation coefficients. So what I'm showing here is the conditional mean spectra, but there are other variants of it, like conditional spectra, where we don't just select the records to match the mean, but we also select the records to have a proper target dispersion in the periods other than the conditioning period. There is also the GCIM, where the records are selected not just accounting for the spectral shape, but also for the other intensity measures such as duration or areas intensity. There is also CSMR, which means that we not only care about the spectral shape, but we also care about the magnitude and distance of the record. So we select the records so the distribution of the magnitude and distance is in sync with the distribution that we have in the disaggregation. So this is a state of the art. Now also, in some cases, records are selected not to match the CMS or CS, but they are selected to match the uniform hazard spectra. So I will just quickly show basically how the uniform hazard spectra looks, because we will mention it later. On the left, I'm showing the CMS for the return period of 475 years for different conditioning IMs. If we match these different curves in their SAT1s, we will get uniform hazard spectra. So all the points in the uniform hazard spectra have the same return period. If we select the records with uniform hazard spectra, we are selecting the records to match this shape that is kind of unrealistic, because in reality we don't have usually the records that have this kind of a wide spectrum. So once we select the records, we can move to deriving the fragility curves. So I'm showing here the selected sets of records. Let's say we have 30 records that we want to select to match the conditional spectrum in this case. For this one intensity level I'm showing here, and then we do this for multiple intensity levels. For each intensity level, so 30 ground motions in this case, for 6 stripes or intensity levels, we run the analysis and we get the response. In this case, I was interested in ductility, so that's my EDP. So this is basically the multiple stripe analysis. So you can see that here, for example, pretty much in every single stripe, you can see that we have scatter, right? So these points, even though that they have the same conditioning IM, they are giving us different response. And this is happening because the conditioning IM is not sufficient, because the other properties of the ground motion are also relevant. And the uncertainty in this relationship, so this scatter that you do see, the relationship between IM and EDP depends on the number of records that we have in a stripe. So how do we decide how many records we want to run? That's something that we want to answer. Also, when we run these analyses and we get these fraction of records that cause the exceedance of an EDP, in my case, this red dashed line, and based on these fractions, we derive the fragility curves. Usually, not always, not necessarily, we assume that the fragility curve is log normal, and we use, in case we use the multiple stripe analysis, we usually use maximum likelihood method to find the median and the dispersion of the fragility. What is important to remember is that the median and the dispersion of the fragility are only the estimates. They're not the true values. And these estimates, they depend on the, as I was mentioning, the number of records that we have in a stripe, but they also depend on the number of stripes that we are running. So in ideal world, we would run as many records as we can. So we'll have a lot of records within a stripe, and we will have a lot of stripes to run. There are, however, two problems with this. One is to find that many ground motions that are hazard consistent, that match our conditional spectrum. And another one is that even if we manage to do that, if we are running this on real structures, a 3D complicated structure, the computational cost would be very heavy. So what we want is to focus on three things, which is first, we investigated how the choice of the methodology affects the number of analyses we want to run. So here, I mean, if we select the records using the UHS and if we select the record using the CS, then the second one is how many records to run per intensity level, and lastly, how many intensity levels to run, and how to choose at which intensity levels to run the analysis. So our goal is to run as few analyses as possible, but still get the reliable fragility estimates. So now Pablo will talk about the more practical part, so the study that we did to try to answer this question. Go.
Thank you. Thank you, Nan. So yeah, I will talk about a little bit about these three studies that we made trying to address these questions. The first one is a comparison between using uniform hazard spectra ground motions and conditional spectra selected ground motions. Of course, conventionally, we do not use uniform hazard spectra paired with multiple stripe analysis, but still we wanted to see what kind of differences would come from using these two methods. So for this, we took the Metis case study site, and we defined a set of simplified single degree of freedom systems. And we perform record selection for multiple stripe levels, doing spectral matching of the UHS, which is here, and selecting with the conditional spectra. Of course, when we do spectral matching, we modify the ground motion shape the content to match the uniform Hasse spectra. This was repeated, of course, for all the stripes, and then we assess the results in terms of incremental number of stripes. So we first just ran a few number of stripes. It would be more common with what is done in practice for nuclear components. And then we increase the numbers of stripes to try to see if we get any issues of stability and how the analysis behave. So here in the plot in the bottom, we have for a collapse damage state of one component, the results that we get of running only 4 stripes of the uniform Hasse spectra selection, which is what we see here more to the left, and using the conditional spectra selection. Additionally, we have a reference or benchmark case in which we run 25 stripes using conditional spectra to have it as somehow of a baseline. Then what happens is that conditional spectra is already kind of close to the benchmark, and it remains more or less stable. This is since we are using the full dispersion that comes from the distribution. So what we have in simple terms is that given the unrealistic shape of the UHS and also the reduced variability that we get with spectral matching, we get steeper curves, which is what we see in the plot. But also it's important where we put the stripes, because if we then add additional stripes, as we can see, the UHS curves shift by quite a bit. Then we add a bit more stripes, and then there's still a bit of a shift. This happens because, again, this extra steep results or a more aggressive shape can lead us to having less usable points than what we have when we use the full distribution of the conditional spectra. So this figure here in the middle illustrates what would be some of the ductility or response values that we get from running certain number of stripes. In green we have it for the conditional spectra, and in red for the UHS. And as we see, we have a bit more dispersion, of course, with the conditional spectra, because we are not suppressing that variability. And therefore, we have some more, let's say, usable points in the fragility result. This can be an issue if we, for example, don't pick well where our stripes are, if we were to not have a good, let's say, a good definition of where the collapse point or where we exceed the threshold, then we might miss those points if we use this very constrained and very steep results. This then goes and can become a problem in the estimation of the response hazard curves, which is the one we have here in the bottom. We can see that if we have large difference in the estimation in the response, we end up with having large difference in the rates of exceedance of a given response. This, of course, can be mitigated somehow. What we found is that if we here in the top in the response we add a lot more stripes, therefore we start closing in which are collapse point and in which points both methods kind of cross the threshold. We start seeing an improvement in the rates, and we end up with similar rates as we now more accurately can find between all the methods the same collapse point. So the main conclusion in this first study was that if we don't have like a very good representation of the hazard with all the uncertainties that it has, we might need a lot more stripes to describe the response hazard and the fragility. The second question was how many records per stripe are we going to run? This impacts a lot if we need to run very complex models in which we cannot afford to run maybe 30, 40 records per stripe. So we wanted to evaluate how many records would be fine. So for this, we defined a case study with a single degree of freedom system in a location in central Italy. We had a hazard discretizing 10 intensity levels going from 40 to 25,000 years. And we selected records in 6 different groups. These groups have different numbers of records in each. So we had a group N3 with 3 records, N7, 7 records, and so on until 44 records. And we perform record selection using the CS method and using the SAT1 for these groups. And again, to measure the variability that we might have, because maybe if we only select 3 records, there are many combinations of 3 records that can match the CS. We repeated this 20 times. So in the end, we have 20 sets of 10 intensity measures for all these numbers of records. The first part that we wanted to see was to measure how well are we matching the target. So for that, we use the sum of square errors that considers both the fit of the median and the dispersion of the target CS. Here we found an acceptable threshold with some parametric testing of around 0.12. And here we are plotting the results of all the 20 sets. So for instance, for the group of 3 records per stripe, we'll have 20 points in the scatter here for all of them. And what we see is that for all cases, when we have very little number of records, we do have higher errors because then we are not able to fully capture all the distribution in the conditional spectra. While if we move on to higher and higher number of records, we can match the full distribution more accurately. This is true for all intensity measures. Of course, in the final intensity levels, when we have very strong motions, the groups with 44 or a lot of records are not able to properly match the target spectra, but that's just because we run out of records that are different and are also matching this spectra at this level. So now that we know more or less how many records we need to actually match the spectra, we want to see what's the influence on the fragility. So we derived fragility curves. We did the nonlinear response history analysis with all of these ground motions on the simplified systems, and we defined some arbitrary thresholds of damage states based on the ductility, where we would expect more or less light damage at a ductility of 2, then at a ductility of 3 we would have some moderate damage, and assuming collapse for this system at a ductility of 6. And using the maximum likelihood method, we can estimate the fragility curves. Now, the results of this, here in we have some figures representing the results that we had from the fragility analysis. For each column, we have the different damage states, and then for each row, we have an increasing number of records. So we would have damage state 1 on the first column, damage state 2, and then damage state 3 on the last column. What we see are 2 trends. One is that, of course, as we move into more nonlinear range and the response of the systems become more unpredictable, and the conditional IM might not be as sufficient for when we have period elongation or something like that. We have more spread in the resulting fragilities, which is what we see in all the cases. And then if we see the figures from up to down, we can see that the more records that we have, the estimate of fragility becomes more stable. So we get the same result more or less for all damage states and for all curves if we keep going with larger sets of records. This can also be seen for all the cases. Here, these figures represent the median and dispersion, so the main parameters of the fragility represented for all the sets and for all the different 20 iterations of these sets. What we see is, again, that if we go from left to right, we have 3 records all the way to 44. What we see is that the spread here becomes much smaller as we move forward on the number of records, as we increase the number of records. And we see the same for dispersion. We get more stable estimates and lower overall covariance of these parameters as we make larger record sets. We do, however, see that at least after about 11 records, the variability in the estimates is not that large, so we can assume that at around that point we could expect to have more stable estimates. So in this case, the recommendation would be that the optimal choice of records, first it depends on how well we want to match the distribution and how much we could expect this to differ also given the damage states. But 11 records as a minimum seems to be a good estimate based on what we saw here. And now the final study that we did is, now that we know how many records per stripe, which stripes are we going to run and how many stripes do we want to run. For this, we try to find a way to optimize it, and to optimize it, we used Bayesian updating. The idea is to have some prior distribution that it could come from literature or from similar system or empirical data, and then update it with a more limited number of analyses to try to find an acceptable fragility estimate. So the Bayesian updating mainly consists on trying to obtain a posterior joint probability distribution of the parameters that define the fragility. So in this case, the distribution would be of our median and dispersion given the data. And this is computed using the probability of observing the data given these parameters, so given the median and dispersion using a likelihood function. Using this prior joint probability distribution of our median and dispersion of the fragility. And it's normalized by this marginal distribution of the data. Of course, obtaining this value, it's complex to do analytically. So here we use the Markov chain Monte Carlo statistical model, which is what is commonly used in Bayesian updating for similar purposes. Now, so how do we go about it? Well, first, the steps that we follow is to first go and get a prior. This could be either from simplified analysis, such as pushover analysis, or something from the literature that we can have, empirical data, etc., etc. Then the second step would be to run time history analysis at 2 stripes. To now have something to update this first prior. This we found that we would be recommended to you do it at around the median capacity that we had from this prior distribution, and something at a lower intensity to try to have a better estimate of the left tail of the fragility curve. But again, it's not super important where the first 2 are, because the updating will help take care of it on its own. So we run these first 2 stripes, and we perform Bayesian updating for the first time, and we obtain our first posterior distribution. Then, based on the response that we have, that would be, for example, we run these 2 gray stripes. We perform linear interpolation to assess where more or less the response we could expect it to be for another stripe that is unknown. And using the estimates of this interpolation, we can find another probability point for the probability of collapse of that stripe. We repeat this process for all the stripes, so we know a probability of collapse in each of the stripes, and we do a Bayesian updating on each of them, which we then compare with the prior distribution. So whichever of these stripes caused the largest change would be the one that we could expect to have the most weight on the future or on the posterior calculation. And therefore, that is the one that we choose to actually run the time history analysis and perform the real updating. Once this is done, we repeat the process again, finding always the interpolating values, now with an updated response, so our interpolations become more precise and our estimations will become closer to the target. I'll show it with an example because it's a bit complex. Here we wanted to find the collapse fragility of a water pump component that is located in some reactor. This is modeled with just simplified models as a stick model also for the reactor. And we assume that the collapse of this component happens at a ductility of 1.25. The reactor is in the Metis case study site, and we perform the selection for 10 intensity levels. And we did, based on what we found on the previous study, we fixed the number of analyses here to 15, just to always have a baseline. Additionally, we have a benchmark case in which we did the fragility fitting with 10 intensity levels and 40 ground motion, so to try to have something very stable. And for the first prior, we used something simplified coming from EPRI that uses the uniform hazard spectrum to compute and to define a first fragility curve for this component. So this fragility curve for the first component will be the blue line here, that is the first prior, and the benchmark with all the 10 intensity levels is the red line that we see here. So as I said before, we run two stripes at around the median capacity, which are the small dots that we see there in the zero, and using that first amount of data, we perform our first updating, and we obtain the first posterior, which is the gray line there. As we see, it's still not very close to the mean, but that's what the Bayesian updation will do. So now we run the algorithm that I described in the previous slide using the linear interpolation, which gives us the most, the stripe that will have the most pull in the fragility curve, which would be the point that we see there at around 0.6 and 1. So that's the stripe now that we run. We perform updating. Now the prior is the posterior of the previous distribution, and now the new posterior, as we can see, is already almost on top of the benchmark case. We can repeat this process again and again, and finding that the fragility becomes very stable. So the estimate becomes very stable rather quickly with few iterations. There in the plot, I also have a dashed line that is showing the conventional approach. So without the Bayesian updating, if we only fit using the maximum likelihood based on the information that we have without taking into account the priors, we can see that the convergence is slower. It takes a few more iterations. So what we saw here is that this Bayesian updating can actually help to get the stable fragility estimates with using a smaller number of stripes. So just to sum things up, some conclusions, it will be that first, as Neven has said, enforcing hazard consistency is essential. Otherwise, we might get some bias due to some information that is not in our chosen IM. The second is that the estimates on the fragility curves might depend on the number of intensity levels and the number of records in those intensity levels chosen. So we get different what we saw of using the UHS versus CS in this somewhat strange example is that we do need more cases on the UHS. So if the records are not realistic or don't consider all the full distribution, we may not be able to capture with a small number of analyses. The optimal number of records should be or can be small, but not too small. Otherwise, we lose the fragility, the stability of the fragility, and also the match with the target. And that this Bayesian updating methods may be a way to find more optimally the position and the number of stripes that we use for fragility estimates. And that would be all. Thank you.
Thank you. Any question?
Thank you for the presentation. Very interesting work. I think it looks like a very massive work was done here. I have actually a lot of questions, but I'll try to constrain myself to 2 or 3. The first 2 are regarding the selection and scaling of records. So you use the conditional spectra and not the conditional mean spectrum, right?
Yeah, conditional spectrum.
Conditional spectrum. So in the conditional spectrum, you have a mean value and a dispersion. Do you scale the records at the period of interest? Do you scale them to match exactly the mean value, or you allow them to have dispersion to mimic the actual dispersion because at this period you also have some dispersion?
Yeah, I mean the conditional spectra here we do scale the records. We try to keep the scaling factors not too high to not modify a lot. The spectral shape is the same. It's maintained for the record, but it's only scaled to match the value at the period of interest. So just at that ordinate, we do have the same value, but at all other periods we have.
Yeah, so the scaling is similar to what you would scale for a conditional mean spectrum, let's say.
Yes.
Yeah. Okay. The second question is because you were showing a scaling or conditional spectrum for a period of interest. Do you keep this when you do multiple stripe analysis? Do you keep the same period for all damage states?
Yeah. In this case, if we do selection like this, and for these simple systems, we kept only the first period as that. But it can also be done, for example, using the average expected acceleration. So we have a range of periods in case we want to consider.
Yeah, because if you have let's say a very ductile building on a soft soil, you may have
an
elongation 4 or 5 times between.
Yeah, in those cases, averages say if you expect that to be the case, averages say would give better results than SAT1 for sure. Okay,
and the last one, it was very interesting, this thing with the continuous or gradual Bayesian update of the selection of stripe intensities. But do you consider what is the effect on the risk when you choose the stripes? The stripes. I'm asking because when you do maximum likelihood estimation, very often you see that your curve that you get is not passing through any of the. It's approximating any of the intensity values, and if you want to, with maximum likelihood estimation, even if it's penalized, you're trying to fit the whole curve, basically. While this may cause you problems. For example, you see this pump that you have. If you put it in a normal building, that is normal industrial building, it will be designed for 1,000 years earthquake or 2,500. You will be interested in the low intensity measures, in low intensities. For example, 0.5 G, 0.3, 0.7. If you put it in a nuclear power plant, for example, in Slovenia or in California or whatever it is, high seismicity will be the right tail of the distribution will be of more interest. So, and if you're not matching all of this, you may have significant bias in the risk.
Yes. In this case, we didn't go all the way there, but Yeah, in this case, we would, for instance, weight more one part of the curve when we compare the differences where we find more stability on perhaps if we're more interested in the left side, we weight it more when we do the comparison between the curves. So that could be, for example, a way of doing it. And also which would be your potential stripes. So depending on the level of the building or what you want, the potential stripes that you could pick from maybe would be from higher intensity or higher return period or lower. But yeah, thank you.
Okay, thank you.
Okay, we have time for one more question. Maybe two. Okay.
Your comparison with the UHS, so we know it's going to suppress some of the variability, but that's not, what you're showing is not common practice in California anymore. We maintain, the UHS goes for the average horizontal, the row D50 ground motion typically, and we impose the variability of the two horizontal components about that. So you won't see anything where everything is matched tightly, and that will flatten out your fragilities. It still won't have as much variability as the CS, but I think you want to try to compare to what practice is now. This is kind of practice 15 years ago, and we don't do this anymore.
Thank you. Yeah, I wanted to do the comparison, but yeah, it was to some older practices. Thank you.
Okay.
Yeah, we can also talk later on, but I wonder whether 11 ground motions is really sufficient to make sure that we have hazard consistency, because, I mean, the goal is to fit the mean and the standard deviation of the conditional spectra. You checked that, and I guess that's good. But hazard consistency means also that you can reconstruct the hazard curves. And to my experience, I wonder whether 11 is really enough to reconstruct the hazard curves from the selected ground motions.
Yeah, I mean, the selection takes into account the hazard curves. All the ordinates come from there. So we assume that the method remains.
Might be good to check.
Yeah, we can do check that.
Dimitrios, I think we have a couple of minutes. Yes.
Okay, quick comment, and that's not unfair because I'm supposed to be part of this sometimes, so I can talk to you later. Anyways, when you want to idiot-proof the method, it might be good to, the reason being that if it's elastoplastic, let's say, and then somebody runs too low stripes, they can pretty much find that their ideal regression fulfills a false prophecy that everything is linear. So it would be good to have stipulated like a need to have always a straddling of the damage state median, for example. In this way, no matter what, you'll be sure that they've not missed some late stage nonlinearity. That's one recommendation. Other one is perhaps this, and I'm pretty sure you know that the 11 motions, maybe if you go to a more complex structure, they may need to be a bit higher, I don't know, 13 or something, which is single degree versus MDOF, but
yeah,
the basis seems to be pretty good actually. Minimum of 11 plus.
Yeah, 15.
Yeah.
Thank you.
I also have many questions, but maybe I just ask one, like a comment. You might some challenge about the selection of the recordings because of the available data. And I was doing the physics-based numerical simulations, so probably it could be
solution for
sure, yes. For explore the fragility curves based on physics-based numerical simulations.
Mm-hmm.
Yeah.
Okay, thank you.
Thank you. Next presentation is Zeynep Gulers. She's going to present on IAEA initiative related to seismic hazard analysis for nuclear installations.
Thank you. So first of all, I would like to thank to Marco and Irmela for the invitation and for the opportunity to present our ongoing activities related to seismic and fault displacement hazards. I will try to summarize the activities that we are doing now, and I will try to go into what we will try to do in the next couple of years. So for those of you who don't know the IAEA framework, the external event safety section is the section in IAEA who deals with and responsible for all the external events that occur in a nuclear installation, including the seismic activities, volcanic activities, any meteorological or hydrological hazards, any human-induced events, geotechnical hazards, and geological hazards that we may expect in a nuclear installation. So our activities cover the site selection process of the new installations, the site characterization, all the way up to the design and safety assessment for nuclear installations. For all of these hazards, we try to serve the member states by providing them safety guidance documents. They are SSG documents, and as you may see in the table on the screen, there are different SSG documents for different levels of the project and different hazards. The safety document related to the seismic hazard is SSG 9, which has been updated in 2022, which means the consultants and the member states has been working on this for the last 5 or 6 years. Our updates take 5 or 6 years to be completed. So this document is a well-received document with the international community, and in most of the member states that is used as an overarching document over the national regulations. I would say maybe except for US, because in US, in nuclear projects, they follow the US NRC guidance, but for the rest of the world, they pretty much follow our guidance in nuclear projects. As these are global documents and overarching documents, they need to be consensus documents. So the statements that we provide in the SSG documents are sometimes quite vague. We cannot say, for example, how many gram motions that you are supposed to use, or we cannot give you a factor of safety for a geotechnical hazard. So we try to fill in this gap by publishing timely technical documents that sort of collects the good practice in the international projects and show the other member states how can you do this, how can you fill the requirements that we give you in SSG 9. So what you see on the screen are the 4 ongoing projects right now to sort of fill in this gap with some technical documents. The first one is related to the PSHA. It's a document on evaluation of PSHA based on observational data. The second one is a safety report, a higher tiered document on epistemic uncertainty and expert elicitation, again related to the PSHA framework. The third one is a technical document on ergodicity of ground motions or non-ergodic ground motion models. And the last one is a benchmark that we are currently undertaking related to the fault displacement hazards. So I will go over them one by one very quickly. The evaluation of PSHA based on observational data document has a long history with us. The document has been started drafting in maybe 2017 or 2018, and based on the community's decision in 2 workshops, one in Pavia, as I believe, and the next one in Saclay. And the intention to develop this tech doc was announced in 2017, and there was a series of consultancy meetings to develop this document. As this evaluation of PSHA based on observational data is the topic of the afternoon, I'm not going to go into the details for this practice, but I will just try to answer these 3 questions which are special to the nuclear applications. The first one is, what is observational data? Where can the member state find the observational data? The second one is, what is the new observational data? As in a nuclear project, we are supposed to use all the available data during the seismic hazard assessment. So what is new and what is available data? And finally, what is there to evaluate? What are we evaluating? Are we evaluating the logic tree, or are we evaluating the results of the PSHA? So this document tried to answer these questions. So in the document, we clearly define 3 types of data. The first one is, of course, the ground motion data recorded on the nuclear installation site. For majority of the member states, this is standard practice to put a seismic monitoring network at the beginning of the site selection process to record whatever is available at the site. So this is a very easy to use data because no conversion is necessary. We just need to get the data together and put it in a flat file, so to say, so that it can be used in several applications of evaluation. However, we realized that while we drafted this document, we realized that we don't have any guidance for the seismic monitoring networks in member states. We get a lot of questions on how many stations are needed, are they supposed to be broadband or ground motion stations, what will be the azimuthal coverage. So a new technical document on seismic monitoring is now being drafted by IAEA. The second data is microseismic data. Norm mentioned that for a little bit. It has a fantastic azimuthal coverage, so it will be used, may be used in evaluation of PSHA. However, the conversion is a problem. The data is collected for a long time. That comes from different types of information. However, the conversion to the acceleration is necessary, which brings in several issues related to its uncertainty. But there are different ways to deal with the uncertainty, and we discussed that in this document. And the last one is the geological data. Anna, I'll talk about this in the very first day. So the data from fragile geological structures may be used for evaluation of PSHA. A good example is Diablo Canyon. So we try to provide these good examples in the IAEA document. One useful graph that we put in this document is at which return period that data will be useful to you. So we can say that the fragile geological information like balanced rocks can be useful for you to up to the 10K return periods, but the other type of data may not be very valuable for your evaluations for 10 to minus 4, which is the relevant return period for our nuclear projects. And finally, this is a discussion that we've been having for at least 3-4 years. Are we talking about the new or existing data? And I think that was a challenge that has been resolved in many meetings, because the idea here is that if you are running a PSHA for a nuclear installation, the quality assurance processes force you to use all the available data that you have in the nuclear installation site. So can you use that data again for testing the PSHA? Or what is the time frame that we are talking about? So we clearly give or explain that the data may be used in developing the seismotectonic model, but the data like microseismic intensity can be also used for evaluating the logic 3 branches. And there is a big time between the shock procedure starts and the safety analysis report is released. And within that time frame, you may get wonderful amount of data from the seismic monitoring network. So you can still use this for evaluation of PSHA. So all of these details you can find in the new document. I believe this document will be out at the end of this year after several rounds of reviews, plagiarism checks, technical editing. It's a pain to publish something in IAEA. So it goes and goes and goes in serious rounds of publication processes. But I would like to mention 2 names. One is Emmanuel, sitting in the back, who collect together all of these experts and make this document happen, and also Doğan Şeber from USNRC, who spent a valuable time on this document. So the next document is a safety report on the evaluation of epistemic uncertainty in seismic hazard assessment for nuclear installations. I find this document very valuable because this is a document that focuses on 4 important things. 1, where does the uncertainties come from in PSHA? 2, does data compilation helps all the time? 3, how do you develop a logic 3 for a PSHA? And 4, how do you use the expert elicitation for the logic tree development? As this is a very, practical document, I want the best of the best as consultant teams, so I try to find the people who did this procedure before in applications. So the list of the consultancy group you see on the screen, and it's increasing because many other people are also expressing the interest to join the drafting group. We did the kickoff meeting last year, and the first consulting meeting was also in 2022 to develop the draft table of contents. I will just quickly go over the draft table of contents. In section 2, we try to give a clear definition of epistemic and aleatory variability terms, and then we try to explain what are the possible sources of uncertainties in seismic source characterization models, ground motion models, and also in site response analysis. And we try to touch base with all of the parameters that are used in seismic hazard assessment for that sense. In section 3, we talk about the data to be collected. How do you create a consistent data set at the beginning of the project, and how to identify the discrepancies in data integration. And then we sort of suggest a gap analysis of the data set and a pilot model to find out what's the data that's missing at the beginning of your PSHA. And then the sensitivity analysis, how to choose the experts for right data compilation, how to build the ground motion models and other stuff. But I think the underlining thing or most important thing of this chapter will be the trade-off between the project schedule for a nuclear project, resources and data compilation. So there must be a time to freeze what you have done and start the seismic hazard assessment, and this is what we are trying to describe in this section. Section 4 and 5 is related to expert elicitation. USNRC has a very clear set of guidelines for expert elicitation in SHAC guidelines, but it's not very well applied in all the international projects, so we try to give very clear guidelines on how to find the expert, how to train the expert, how to help them make educated guesses or decisions, hazard-informed decisions on seismic hazard assessment process, starting from the beginning. We did not make a lot of progress in this document, I have to say, because I wanted to pause for a little bit. I think we are doing so many things in the same time, and for each one of these documents, we are trying to get different consultancy groups, which sort of create some overlaps, and almost the same things are written in different documents by different people, so we are giving, not very clear messages to the community. So as this is the higher tier document, I plan to stop for a year and try to finish the other ones, and now we are going to move on with this document in 2024 with the 2 consultancy meetings. Let me continue. The third document is the technical document on ergodicity of ground motion prediction equations for nuclear installation sites. Norm gave a fantastic speech on that, so I don't need to add anything else. However, every time I do this presentation in the nuclear community, people say, what is an ergodic approach? So I try to explain them in very basic words. What is the ergodic assumption? How can you remove the ergodic assumption? And I'm proud to say that majority of the curves and simple equations that Norm has presented are now included in our tech doc. And this simplified language comes from the need for me to understand what's going on. If I can understand it, possibly everybody else can understand it. So Norm helped us a lot to simplify the language and different types of models to be used in non-ergodic framework. So all of these simple sketches and very well explanatory equations are now in the IAA document. So this clarifies the terminology with simple examples, explains how the strong motion data is completed for building a non-ergodic ground motion model, and the support provided by ground motion simulations is also in the document, describes the methodology step by step with clear equations, and we try to provide some examples from the nuclear community, like the CRISCO NPP case where the non-ergodic ground motions are implemented. So these will be provided in the annexes. This document is almost over. Right now it's in independent peer review with Adrian, so we are waiting for him to finalize his review. And hopefully at the end of the year, this comment cycle will start. However, I would like to invite you to the international workshop that we will perform in June 2024, which we will distribute all the documents that we have finalized to you, and we will try to create some training examples so you can see how these methodologies are applied for simple data sets. So please mark your calendars for the invitation, and if you have any questions, please write me an email. I will do my best to explain to you how to be nominated for IAEA events. The last document that I would like to discuss today is the probabilistic fault displacement hazard assessment document. This is not our first PFDHA document, actually. This is our second. Our first document is already out, but it includes, already available practice in the member states. Sometimes the good practice is not really available to everybody because it's in the nuclear installation reports. So this tech doc actually includes the analysis that's been done for Yaco Mountain, for Diablo Canyon, and for Crisco plants to show you how the analysis is performed for nuclear installations. However, while they work on this document, the Fault Displacement Hazard Initiative has started in UCLA, and new models has been published. So we wanted to keep up with this new activities, and we created a benchmark. In this benchmark, we have a very complicated structure, again. So we have an advisory board who first developed the first benchmark case, which is the Kumamoto earthquake case, which is a strike slip case with a magnitude 6.8 rupture surface. And then the modeling teams include the models that are already there, including Youngs et al. 2003 and Peterson et al. 2011. So none of the new models were included in the very first stage. The comparison of the results are already published as a paper in BSSA by Alessandro Valentini. You can download the paper. And when you will read the paper, you will see that the results doesn't agree with each other at all. So for a very single case, with different fault displacement models, the hazard curves are all over the place. So then the advisory board decided to update the analysis by saying that why don't we include the new models published by UCLA Initiative, and why don't we add two more cases like the Norcia case, which represents the normal environments, and the Letail case, which is a reverse earthquake, a small magnitude event, but still has some surface ruptures. So I will show you one by one. This is the Kumamoto case, which has three segments. And in the benchmark that we provide to the hazard analysis, we create such a complex, benchmark case, it's almost impossible to compare the results. So we have multiple segment ruptures. We have a single branch logic tree, a multi-branch logic tree, not a very smart way to run a benchmark, in my opinion. So I'm going to show you very simple cases. As you see on the first one, this is a hazard comparison for a primary fault displacement. As Paolo explained yesterday, primary fault displacement is the displacement that occurs on the fault itself. However, this is not our main interest because a nuclear installation cannot be built right next to a fault. So we need to be at least 5-7 kilometers away from the fault. So this creates a very big, range of hazard curves, 5 or 7 kilometers away from the fault. So you will see that our primary faulting benchmark has a good agreement between different modelers, but especially for the distributed case, the amount of dispersion is unbelievable, and this is going to be a hard document to publish based on this big differences in the current models. Kumamoto case, let me move on to the Norcia case. Some of these results are updated. This slide is maybe from 2 months ago. I can say that we have some updates in the primary displacement case, and the primary displacement case works quite well. The results are agreeing very much with each other, but the distributed case is again quite different. We need to understand the underlying reasons of these distributed displacement hazard curves. Otherwise, it won't be possible to provide the guidance to the member states in choosing the models. Letail case, I don't even want to show that to you because it's a magnitude 4.9, okay? For majority of the empirical relations don't even give you a probability of surface rupture. It's an extrapolation that maybe nobody else considered up to this point. So the results are really not agreeing very much. So for this document, I'm going to need at least 6 more months. But right now what I'm doing is I'm writing all the modeler teams and say, your hazard curve doesn't agree with the others. What are you going to do with it? So I'm just telling them, this is this activity rate where your hazard curve needs to start from, why your hazard curve doesn't start from there. So it's an ongoing interaction among the modelers. So the final remarks is, an initial draft is ready for this one, and Alessandro did a fantastic job in this draft with many contributions from several geologists and modelers. We had one CS meeting this year, and we have tremendously learned from this exercise on the impact of the parameters and the logic tree structure. And we are hoping to finalize this comparison and discussions in the next year. A new chapter, by the way, is added to this tech talk by Emmanuel again on the engineering implications, because if you have a fault displacement of 10 centimeters, how are you going to handle this? Do you have a fragility for fault displacement? Do you have any engineering measures or implications for fault displacement under the reactor building or in the water intake structure? So that sort of guidance is missing, so we are trying to have a first attempt to capture whatever is known in the current practice, but we will need some time. And I'm hoping that this summer in the training course, I will have a better version of the hazard curves. So these are the ongoing documents that we are working on to support SSG9. However, I would like to introduce you to the discussion of the year, which took a lot of time of the external event safety section, and this is related to the grading of PSHA efforts for intermediate hazard facilities. I will give you a simple background. I can say that the small modular reactors can be considered as intermediate hazard facilities, and a simplified methodology is needed if a country would like to build a small modular reactor. And this simplified methodology is given to the countries in sort of a handbook for site selection and site evaluation. This is a roadmap, a very simplified thing for the first-time licensees and first-time licensing countries. So this is not for maybe experienced member states, but there are several member states who haven't done a large-scale nuclear reactor up to this point. They would like to start with an SMR because it's easier, and it's faster, and it's cheaper. So SMRs are attributed to lower inherent risk, and SMR site may be considered as intermediate radiological sites. For such a site, are you going to do a full shock level 3 analysis? If you will do, you will take quite a bit of time, and the project will be quite costly, and the community is looking for a less costly, I'm not saying cheap, but I'm saying less costly, and shorter seismic hazard assessment for these sites. So I would like to acknowledge again Norm and Paco and Philippe Rino and Doğan Şeber for all of the discussions, and we have developed a very simplified methodology that may work on SMR projects. What are we giving currently as guidance is 2 simple statements. In SSG9, we say that if you have an intermediate radiological hazard facility, 1, you can do the seismic hazard assessment as for a large-scale reactor, but you may adopt a lower input ground motion. Instead of 10,000 years, you may go to 5,000 years. Okay? This door is open. However, if you want to go with this statement, then this means that you are going to still run a full-scale PSHA study, but you are going to get a smaller return period, ground motion with a smaller return period. This might be good if the facility or if the site has already have a PSHA report. Some of the SMR sites are on brown sites where there is already something going on, but for the new sites, this is not feasible at all. So for this case, we have option number 2. Option number 2 says, if the methods for a regular MPP are disproportionately complex, time-consuming, and demanding, simplified methods based on restricted dataset may be used. So for the new sites, it's clear that everybody wants to go to option 2. So we are going to use a simplified method based on a more restricted dataset. How and where? So can we do it everywhere? Is grading the PSHA possible using option 2 everywhere around the world? I would say that the SMR designs have their certified design spectrums, and they claim that they work very well for very large ground motion values. They are sometimes designed for 0.5 Gs, sometimes bigger. The seismic demand in the areas of low to moderate seismicity are possibly smaller than these design spectrums. So if you are in a stable continental region, which is crudely Northern Europe, Central and Eastern part of US and Canada, South America, West Africa, and Australia, you probably have quite a big margin compared to the certified design spectrums. So it may be possible for you to do a smaller effort to run the PSHA, but still have this enough margin in your calculations. For shallow crustal and active tectonic regions or in subduction zones, that's not the case. The hazard may be quite high. You don't know beforehand you will have enough margin for the certified design spectrum. So unfortunately, in Turkey, in California, in Japan, there is no easy way out. You still need to do a full scope project because you may have a significant hazard and you may not be safe. But for other regions, particularly in Europe and in US, you may do a little bit less, especially in the site selection and technology selection stage. So I would say that SSG9 never attributes the full-scale hazard to a shock level 3, but in reality, everybody does a shock level 3 for large-scale projects. So if we are grading something, we are grading it from shock level 3. So let's discuss now what we can do to grade down from a shock level 3. So the framework that we developed includes 2 steps. In the very first step, we need a crude estimate of the hazard. Please keep in mind that this step is actually a step where you don't even know the site. Okay. You may 5, 6, 7 options for the site. You haven't chosen the technology yet. SMRs have close to 500 different designs. So you are just in the market looking for a site and looking for technology. At that stage, all you need is a crude estimate of the hazard. And the current proposals say, at this stage, we can do a simplified PSHA for you. What is a simplified PSHA? A simplified PSHA is maybe a PSHA that includes only the nearby sources, maybe a PSHA with a backbone GMC model. Maybe a single zoneless aerial source can be used. Maybe we can eliminate some low-weight branches from the logic tree. So a simplified PSHA is something that you will do quickly, but unfortunately, it's not very well defined. It's not a shock level 2, it's not a shock level 3, it's just called a simplified PSHA. So I believe that the scope of the work for this simplified PSHA is hard to constrain. As the review and assessment continues with the regulatory, they will ask questions, you will ask questions, and this is going to be augmented on top of each other. So if we are planning a very basic PSHA and then try to review it, are we really saving time and money? Because it may take forever to finalize this discussion. So a conservative way of getting this crude estimate might be much easier than performing a PSHA. In many parts of the world, there are very well-established seismic hazard maps. I can very quickly say the USGS National Hazard Map or the European Hazard Map, ESHM, in 2022 is a fantastic hazard map. The seismic source and ground motion characterization models are very well documented and open source and peer-reviewed, and these numbers are being used by the community, so it is something that everybody is familiar to. So can we use these maps in this crude way of estimating the seismic hazards during site selection? I think we can, and personally I believe that instead of going to a basic seismic hazard assessment without a very well-defined scope, going to the map is easier, and I think more straightforward for majority of the cases. However, there are questions, of course. How can I know my map is good enough to do that? Is my map giving me 10 to minus 4? Or the site-specific components of PSHA is not there. How can you tell me to read something from the map and go on with it? And is it conservative? So I will try to give you some answers for that. To get the answer of is it conservative or not, we collected the nuclear installation sites, 64 nuclear installation sites, mainly from US and also from Europe. These nuclear installation sites are located in stable continental regions. The numbers are available to us, and a shock level 2, 3, or 4 has been performed in the last 10 years. I know there are many other sites, but these are the sites that I can reach to very quickly. And what we did is we take the map value for 10,000 year from USGS map or from European seismic hazard map, and then we get the site-specific PSHA value and calculate the ratio. If you look at the red line, okay, that's one-to-one line, and this area is where the site-specific PGA is bigger than the map-based PGA. And you may see that for 66% of the collected nuclear installation sites, the site-specific PGA is actually smaller than the map-based estimate. The map 10,000-year PGA from the map is bigger than your site-specific number, because the site-specific issues or the site-specific properties actually reduces your hazard estimates compared to the map. And for 90% of the cases that we have collected, this ratio is less than 1.0. Yes, your site-specific can be bigger than the map estimate, but the ratio is less than 1.0. So what if I'm looking for a site, if I'm looking for a technology, what if I read the 10,000-year PGA from the map and multiply it with 1.7 to be on the conservative side, and use this as a very crude, very initial estimate of the 10,000-year PGA? Instead of paying the consultant to do a basic PSHA for me at the very first step, I can get this very crude estimate from the map. That's the general idea. So here's the flow chart. So if you follow the flow chart, the first step is, first you need to confirm that your national or regional seismic hazard map can be used for this purpose. And when you read the details of the document, you will see that USGS map and the European map is suitable for this purpose, but we give you a set of criteria that you can use to see if your national map can be used for this purpose. Step 2, if it is, please read your 10,000-year PGA from the map. If the map gives you 10,000-year value, great. If not, we are giving you a very simple equation to convert 475 years PGA to 10,000-year PGA. And then we want you to multiply this number with 1.7 to get a very stable estimate and very conservative estimate. This gives you the conservatism that comes from the ratio from the site-specific to map-based applications. And then please compare it with the selected technology's design spectrum. And if you have sufficient margin, you may choose the site and you may choose that technology. Okay? So this is sort of the flowchart that we provide to the member states who do the licensing maybe for the very first time. If one of these answers is no, you will move to step 5, which is sort of doing a shock level 2. But at the end of this simplified procedure, which you can perform in 1 hour, basically, just read the map value, you can say, you can get a conservative site-specific mean estimate, and you can use it for site and technology selection, and after the site characterization is complete, you will do the real work. So what is the real work? The real work is, again, now the site is selected, the technology is selected, you have started the site characterization, you have the site-specific parameters. At this point, you need to run a site-specific hazard assessment. Because otherwise, nobody, no regulatory can accept a vague number from a map at this point. So we will have a more realistic and less conservative hazard estimate that is needed for seismic PSA. That means we have to perform a shock level 2 PSHA. It's clear that we are grading down from a level 3 to level 2, which brings in our calls for a special attention on the epistemic uncertainty. By grading down our efforts from 3 to 2, are we losing the epistemic range of epistemic uncertainty that we need to consider? So to help you with that, we have calculated, we have taken 28 sites who have performed the shock level 3 in the last 10 years. These are 5 Spain sites and 23 SEUS sites. And we calculate the mean to median ratio for these studies. And I can very simply say that this mean to median ratio is an indicator of the range of your fractals. That's it. It sort of shows you is the epistemic uncertainty is properly treated or covered in the study. And you see on the screen, it depends on the frequency range, of course, but the limiting value is approximately 1.6. So at this step, we are saying that now your site is selected, your technology is selected, you have already performed site characterization, you know your site parameters, please go ahead and do your shock level 2. It's less costly and shorter than compared to a shock level 3. However, we want you to check your mean to median ratio and see if it's less than 1.6 or not. Because if it's less than 1.6, the simplifications you made may not be very sufficient to cover the range of epistemic uncertainty. In that case, you may go ahead and evaluate your logic tree branches, or you can very basically take your median estimate and multiply it with 1.6 for your mean estimate. So all of these details will be written in the handbook, which will be available next year. So if you send me an email, I can send you the related link. And I think this is one of the good services that we are doing this year to the member states, especially particularly for the member states who are interested in SMRs. My last 3 slides, getting ready for the next year. As I'm going to be here for a couple more years, I would like to do more, including what is missing, what is the guidance needed for nuclear installations. And I'm happy to see that following up all the presentations from yesterday and today, I see that IAEA has a very good coverage on what's going on, especially in European practice, and we try to include all of these things in our technical documents, except for one thing, and that's the site response. 2 important documents were published in the last 2 years. One is the document that Adrian has presented, the NRC's shock level 2 site response document, and very clearly show that the site response, the contribution of site response to the tornado plot is closer to the contribution of other factors. So site response is a really important part of a nuclear project, a site evaluation project. This uncertainty in site amplification factors, I don't know if we are taking this into account in every member state. So another one is the Sigma 2 project final report. Sigma 2 project clearly underlined that site response will be a point of discussion for Sigma 3 as well. And there are many missing steps that we can add to the ongoing guidance related to the simplified soil profiles for 1D analysis, vertical plane propagation, uncertainty in the 1D site response, and all of these things. So we know that the nuclear industry will be dealing with the site response in the next 2-3 years. What are we giving to the member state at this point? The IAEA document or the guidance on site response was published in 2016, which means that it's written in 2012, and almost 10 years have passed, and that 10 years, there are a lot of improvements in the site response analysis. And the only site response guidance that we give to the member states is this tech doc, and this is not a site response tech doc. It's the ground motion prediction equations and site response tech doc, and the site response is only discussed in one chapter. And this one chapter, unfortunately, is written quite from the perspective of the simulations, based on the Japanese practice. Unfortunately, current state of the practice in site response analysis is not included in our guidance. So when we did a gap analysis last year, many member states said that we need to know more on host-to-target adjustment methodologies. This is very critical for us. We need to have some guidance on parameters like kappa naught, and we would like to know how the recordings in the site monitoring be included in the site response. We need to know how to do 1D site response for soil profiles with VS reversals or for non-uniform VS profiles. And we would like to, of course, know more about the RBT-based techniques and selection of input motions, the sites for the near or top of the basin. These are the missing points that we have never provided guidance up to this point. So I'm happy to say that we are starting a new site response project supported by many member states next year with a kickoff possibly in April, and we are going to provide a new safety report on site response analysis possibly in 2-3 years. It will be available for your use. So as a concluding remark, I'm happy to be here and I'm happy to listen to all of your presentations, and I would like to invite you, all of you, to be more involved in IAEA work. You know that we are not paying anybody for their work, but at least you can see that your research is included in some practical applications. Thank you very much.
Thank you. Who wants to start?
Thank you for the presentation. I want to have a remark and maybe a modest recommendation regarding this approach for the preliminary hazard estimate. I think it's already what people are doing and will be doing, because, I mean, it's common thing in other critical infrastructure, for example, for dams, when you need to select the exact location, or for chemical power plants. But it's very good to have this in written form from such high-level authority as the international agency, because in nuclear, very often people are much cautious what will be endorsed by the regulator, or, you know, in the US NRC, if something is not endorsed, so it's directly forbidden. So it's basically a sin to do it. So it's good to have such an approach. In my opinion, what can be and may need to be added and expanded, probably in a qualitative way, is that very often you show on your graph with the different site-specific to mapped PGAs or hazards that actually for most of the sites the mapped one is bigger. Mm-hmm. I think for Europe this will be the case almost in all sites. But people, because this will be the start of a hazard assessment, they won't know what are the sources of conservatism. So there could be some written bullet points, for example, to try to trace the sources of conservatism, for example, ergodic versus non-ergodic ground motion, or lumping of fault zones in a single fault rather than multiple faults. Because if you just take this mapped hazard and multiply it by 1.7, 1.5, whatever, you may be very restrictive to some technologies, and actually you just, and this is a very competitive industry now with SMR, so you may remove some potential technology or sites without actually being very robust about it.
Okay, thank you very much for the comment, and I'm happy to hear that, because most of the time I present this, I got a big reaction, because what, are you suggesting that read something from the map and use it? And I try to explain that this is just an initial estimate, and I'm putting the additional conservatism. But what you said is right. If you do not want to eliminate other options, you may go with, and if the site is almost selected, you may do a little bit of site characterization and start an initial analysis, an initial estimate, site-specific estimate, which will be less conservative when compared to the map value multiplied by 1.7. I think we should add this to the document.
You may, I mean, how to say, motivate a bit of a back and forth discussion with the actual developers and of the SMRs, because for some technologies it will be more difficult and more expensive to increase the design hazard, and for others they will be inherently robust, so it's not a big issue. So these things should be understood from the beginning in site selection.
Yeah. Okay, thank you.
Thank you, Zin. I really enjoyed the presentation. And,
thank you.
I have a comment also related to the methodology that you were presenting regarding the use of already existing models. So as you know, we have a mosaic that is global and is incorporating also the European model, the US model. And so I guess that methodology is just to a limited extent probably focused on countries like US and Europe, right? But more probably on areas where unfortunately there's far little information. And based on our experience, I'm a bit skeptical that the existing models that you have in those areas, including the ones that we have, can go down until 10,000 years. And I would argue that based on my experience, also for the European model, despite I also consider that a very good model, there's no possibility of going down to 10,000 years, because the characterization of faults, for example, is for the most part done without looking at each individual fault and, for example, using paleoseismological information. And in some cases, also the way in which the fault itself is defined, as Una was explaining in her presentation, is not, say, representing the physical object. So that is, in my opinion, a limitation in the way in which the models could be used for something that goes in the direction of a site-specific study.
Excellent comment. Thank you very much. I didn't mention it in my presentation, but for several countries, especially for African countries, they don't have a map they can use for this purpose. So in these cases, it's not possible to get a reasonable and conservative estimate from the map. You will most directly go to ESHAC level 2. You have to do that. And for the European map, I kind of disagree, because the 10,000 year and 10 to minus 4, 10 to minus 5 estimates are typically dominated by the standard deviation of the ground motion model, not the source parameters itself. So this standard deviation of the ground motion model that has been used in the European seismic hazard map is pretty reasonable. However, of course, there is room for improvement, and this room for improvement is in the non-ergodic way, actually. However, I don't see a new starter which looks for a site and technology, which needs a quick answer, will go to that in this month or something. But after the site is selected, I think the way to go, especially for European site, is to do a non-ergodic ground motion model, I will say. Others?
Many thanks for the interesting presentation, Zineb. I have a point about the SMR and the relaxing discussion about PSHA. We talked about that already in EIA. And I think one important point is that on top of the decision if we can relax or not a PSHA, is the question should be how far and how it is the design of an SMR. So we are talking about 80 different types of SMR that are in research and development. None of them is in operation. We have many questions on that, and I'm saying that because coming from the nuclear industry, even if the SMR are maybe seen from the public like a different path of the nuclear MPPs, at the end, if we have an accident, this will cause a negative consequence of all over the MPPs in existing operation. And so, in my opinion, the first question should be how confident we are that the SMR design are safe and prone and have the same standard as an MPP. And after the licensing process has been done and some risk assessment has been done, and the seller showing that the design is prone, so we are also confident to see if the earthquake hazard is dominating the accident or not. If it's dominating the hazard, to me, it should be an important criteria to do not relax the PSHA. If it's not the case, so let's do that. But I think at that moment, I think it should not be the pressure of the SMR sellers that will give another approach that we are using in the nuclear industry, because at the end, the nuclear industry is one family, so if something is happening, it could be also a consequence for the new project, even of big NPPs.
You are absolutely right, and we totally agree with you. Therefore, we are right now doing a study on which SMR designs are actually maybe considered as intermediate radiological sites. There are, as you say, so many different designs, and when you combine them with multiple units, some of them have source terms as big as in regular NPPs. So it's not yet so clear which of these combination will result in an intermediate radiological hazard checkbox. So my colleagues are currently working on that. They're trying to develop a framework to see which one of these facilities can be considered in this checkbox. And only if you are in this checkbox, you can go to a simplified methodology like that. So we are working on that, absolutely.
Yes.
Okay, I have a question about fault displacement hazard, of course. You mentioned that a point that you do not provide guidance is, for example, the level of displacement can be realistically relevant. You mentioned 10 centimeters. Mm-hmm. Okay, it's an engineering problem, basically. But I think there is another parameter that can be important also for, can have implications for the definition of the activity of a capable fault, that is the return period. Mm-hmm. So to my knowledge, there is no clear indication which is the level of return period or annual frequency for fault displacement. So are you planning to discuss this and to provide some guidance on which is the reference return period to consider for fault displacement hazard?
For this, we have two benchmarks. One is if a hazard is, if the annual rate of exceedance is less than 10 to minus 7, we screen it. So that's 10 to minus 7 return period is a benchmark number. And the second benchmark that we have is that for geotechnical settlements, a 5 centimeter displacement is sometimes allowable under the base mat. And we know that for Diablo Canyon water intake structures, for example, 1 or 2 centimeters were accepted as the allowable limit for fault displacement. So there are some practices that we can refer to, but unfortunately there is nothing that I can directly give you at this point for the amount of displacement or the return period. I know that some member states, particularly Japan, are running a lot of numerical models to see how much displacement can the base mat stand. And my unofficial information that they can go up to 50 centimeters in design without anything happening to the base mat, because these are very stable structures, you know. However, I don't have currently the right number to share with you. But we are working on it, and we are trying to collect more and more from the ongoing practice for both of these numbers, the amount of displacement and the return period. Am I taking too much, Marco?
I think it's okay. We have,
okay.
We have some time for lunch. So.
Sorry, building upon Paolo's remark, actually there's some evidence coming from work done by the group of Gazetas, and they were showing that underneath heavy mat-supported structures, and actually much lighter than reactor buildings, the surface, let's say, trace of the fault had a tendency to avoid the mat just because of the weight of the overlying structure. So, I don't know. I know it's evidence. It's not perfect, but...
Yeah, as a geotechnical engineer, I'm not very confident in the fault displacement value, if you ask me personally, because I know that it depends a lot on the surface soil conditions, it depends a lot on the local geology, so I don't even know where this displacement, what is the orientation of this displacement, do we? Right, is it in the vertical plane, or is it, so all of these things are very, how to say, vague, unfortunately, in the current practice, and my only solution to you is now numerical models. To try these things.
I want to add something. I agree to the comment that is made, but there is a problem about the vertical displacement. We have seen in the new two earthquakes that had happened in Turkey, for the water tanks, the displacement, 10 centimeter vertical displacement, didn't do anything to the tank, but the water pipes that were connected were totally destroyed, so the function was gone. So we need to really discuss the displacements in terms of not the real structure, but actually the components. So it has to be discussed, but not due to the heavy load of the big building.
Yes, one of the new projects that we may develop in the next year is how to handle this fault displacement in the design of a nuclear reactor building or other safety-related structures, if the member states request it. So at this point, during the last donors meeting, we have presented this idea and nobody was literally listening or requesting a particular study on that, but everything may change in 1 year. So again, next year I can just bring in these discussions on the table and ask, do you need something like this?
Okay, thank you very much for the discussion. Thank you, Gulert. And we're ready for lunch.
Per domani che sono...
No, due precise. Okay, welcome back. British. Let's start with the next presentation. Emmanuel Viallet, presenting challenges in evaluating PSHA results based on observation.
Thank you. Good afternoon, ladies and gentlemen. It's my pleasure to be here with you and to make this presentation in the afternoon. So I have also the duty to keep you awakened after this gorgeous lunch. So I will do my best. And so I'm going to share with you some, be sure that it will not be an exhaustive presentation, so some challenges and recent advances in the framework of evaluation, evaluating PSHA results based on observation, and especially illustrating the benefits of implementing Bayesian approaches and updating PSHA based on Bayesian approaches. And maybe I can just try to start my presentation with an illustration of what could be Bayesian approaches. So you have a prior, and I will use this pointer with a prior assessment, so trying to get, and then trying to rely on observation, okay, and then update and try to make it better. Okay, so this is a kind of intuitive way to update prior estimation. So I will have a short introduction and coming back on the objective of my speech. Then I will illustrate some recent activities in international organizations, including IAEA, OECD, NEA, and other international projects. Then I will try to illustrate some benefits of implementing Bayesian approaches. And I will try to go step by step, because maybe, and please forgive me, most of you may already know very well Bayesian approaches, but I will start with very simple example just to let everyone be online with that. And after that, I will make a presentation regarding, let's say, a full scope PSHA, just to illustrate what could be the outcome of such approaches in the framework of probabilistic seismic hazard assessment. And I will draw some conclusion just before finishing my talk. So then let's start with introduction and objective. So you all know that PSHA is a well-established approach, largely used, can be for site-specific assessment, national scale, even continental scale, for regulatory seismic zonation, critical facilities, especially nuclear facilities, and risk and insurance. There still are some issues of interest, for instance, how to well quantify and clear separating multiple sources of uncertainty, especially aleatory and epistemic one, especially, but not only in area with low to moderate seismicity. We think we have understood that even in Diablo Canyon it could be an interesting issue, but also how to well elicitate expert opinion, and you know chaque approach that is especially built to improve and to make this elicitation of expert opinion as robust as possible. But also, it was a presentation and some presentation, especially yesterday, to develop non-ergodic approaches to improve the PSHA itself, and which could be a way to address the example one I gave just above. And if I should, or if I would try to summarize the level one, or the basic question is, at the end of this process of evaluating or performing PSHA, how confident are we that we have captured the center, body, and range of the technical defensible interpretation? So I think this is the real target, to make sure that at the end of the day, we are confident and we have improved the confidence in this CBR. So in this very quick introduction, the objective of my presentation is to promote the extensive use of observation to improve confidence in PSHA results for multiple reasons, and I will try to illustrate with some useful reference, also to give some example on practical cases. Also to highlight some special care, because there are some special care to keep in mind and to draw perspective. And for some people, for some of you who know me, that I will also try to illustrate the benefits of applying Bayesian approaches, and again taking into consideration the largest amount of available observation, and also pointing out that it will provide PSHA actors with objective outcomes and could encourage them to think, to update, and possibly reconsider their own views or beliefs. So, sorry, I have not too much time, even if 35 minutes is a very interesting time to develop, but maybe I will not have the time to go into too much detail, but I will spread my presentation with some reference that you can get if you are more curious. So, moving now to some recent activities in international organization. So, in a chronological view, I will just point out some activity and recent, even if I start from maybe a first OECD workshop in 2008. This one I will not elaborate too much because 15 years ago cannot be considered as too much recent. But then after that, there was the Sigma 1 project between 2011 and 2016, more or less. Then there was a second OECD workshop in Pavia in 2015, and I think most of the conclusion and some of the paper are still really interesting today. There was the Sigma 2 project, started in 2017 and finished in 2022. As perfectly introduced by Zeynep this morning, there was also an IEA activity in the framework of the External Event Safety Section extra budgetary program work area 1 dealing with hazard regarding the tech doc, which should be published very soon. And finally, Metis project. We are all together today for this, or thanks to the organization of Metis project. So, of course, I will focus, and most of my references are relying on this activity, but there are, of course, many or multiple connections with other research programs and projects. So, let me illustrate this background, starting with OECD. So I already mentioned the recent workshop, 2008, 2015 in Pavia, so not too far away from here. And for the main conclusion, I will try to summarize. There are three main conclusions. That first, an activity should be launched to compare seismic hazard analysis from area, from various and level of seismic activity. This was the recommendation number one, and following this, there was an OECD activity that addressed this recommendation. Then, encouraging PSHA actors to test or to evaluate results based on observation. And especially focusing that the fact that this assessment should not only focus on median or mean hazard curve, but should explore the whole range of the PSHA, so the whole logic tree of the PSHA. And finally, the last one was to recommend to develop common guidelines to help the community to apply to this kind of evaluation based on observation, and this is exactly the starting point of the IAEA activity. I will come back to very soon. Then, and you have two references here of OECD workshop conclusions. Then from IAEA, so as already mentioned, perfectly introduced by Zeynep, but I just would like to mention here that there are one recommendation or requirement coming from the SSG9 revision 1, which I just copy-paste here, that encourage and recommend to perform evaluation based on observation, either for consistency checking or for improving the weight of the branches of the logic tree. So this is directly coming from the SSG9. And no surprise, but the activity that was mentioned by Zeynep and one of my chronological view to the activity regarding the development of a new tech doc, which name is Evaluation of Probabilistic Seismic Hazard Analysis based on observational data. So I will not go into detail. I hope that this tech doc will be issued very soon. But though this especially addresses the recommendation number 3 from OECD 2015 workshop, but also support the section 6.13 of SSG9 revision 1. And for that, the tech doc elaborates and explain and discuss multiple steps of the approach, including different types of observational data, including instrumental seismicity, historical seismicity, and paleoseismicity. It also includes the possible way to perform evaluation based on observation. It could be at an elementary step of the PSHA, so meaning that we can evaluate, for instance, seismic source characterization model, could be GMPs, or any single step of or branch of the PSHA, but could also be used as an integral evaluation, meaning that the outcome of the whole logic tree, including the combination of multiple elementary branches to each other, in order to make sure that especially this combination of multiple branches does not lead to unlikely results. So this is also well and detailed in the tech doc, the IAEA tech doc. It also includes the definition and some possible use of observation, such as consistency checking, so just checking that the results are consistent with the input data. But it can be also included in a weighting process to improve, to change, and to update the weight of the branches of the PSHA and the logic tree. It also introduced the concept of area-based approach, meaning that it's possible to gather multiple observations from multiple sites in order to improve the efficiency of the process. And I think all of the actors that were involved in this activity all expect that tech doc will be published very soon. Then, let me now focus on the benefits of implementing Bayesian approaches. And I will have a step-by-step introduction, so again, forgive me if it's really obvious for some of you. So, Bayesian theorem of conditional probability was developed in the second half of the 18th century, largely used now by academics, by industries in a wide range of disciplines. Can be earth science, natural hazard and risk especially, but not only, of course. In my opinion, still need to be promoted, so that's why I'm here today, and I will continue to promote this. And I will go into more detail, don't worry, but if you are interested, you can visit the website of the ISBA, International Society for Bayesian Analysis, or personally, I recommend to read some books written by Gordon Wu, who develop not only, but some consideration regarding this question. Again, you have the link if you are interested. So, let's start with very simple cases. So, let's work on dice throws. So, it can be very simple, but you will see that we can also complexify a little bit the exercise. So, I will have 3 examples. First one, it's easy. Let's assume that we have only 1 dice in hand, but the number of faces is unknown. So in my example, we will have either 1 dice of 6 faces, 1 d6, or 1 dice of 12 faces, 1 d12. So it may be very obvious. If the first result is 8 or 9, no need to have a Bayesian update. Oh, I've just lost my... I've lost the view on my screen. Do you know how to do that? To get it again? Sorry for that. Should I? Okay. Yeah, thank you. Sorry. But I will use this example with throwing a 1d6 just to see how it works. Then a little bit more complex case. Let's assume that we have 2 dice in hand. Could be 2 dice of 6 faces or 1 dice of 4 plus 1 dice of 8. This is interesting because we have no way to exclude one or the other because it will always give either a result between 2 and 12. So Bayesian updating can help on this. And I will finish, and I will check the time just to make sure that I'm not spending too much time on that, with a more complex case. That maybe, and the more complex is that we will have n dice, n being unknown, and of possible multiple combination of dices inside. So, and this starts to look like PSHA, but you will see by yourself. So, before going to the example, just reminding the principle. So, to apply Bayesian approach, we need to have a prior model. So, we'll have to include in the prior model the possible situation depending on the 3 cases I will use. Then we need observation, so it will be the results of the dice. And then we will apply the Bayesian theorem, so and then we'll get the posterior model, so P of A knowing B, and updating the likelihood of any single branch of the model. So meaning that for that we are going to assess the probability of observing B knowing A or any AI of the prior model. So to do that, and you will have the numerical application just after. So you will see that this is my own tool for that. It's I will explain all the part, but we'll have here, for instance, the updated likelihood of any single branch. Here we can have an illustration of the proportion of the likelihood of the updated likelihood from the less likely until the most likely. Here we can have the prior model, I mean the whole logic tree of the model can be very simple in the first case, will be complicated in the last one. And here you will have the evolution of the confidence interval along the multiple results. So based on that, we will see how the updating works. And again, the main outcome, expected outcome, is to update the likelihood or the weight of any single branch of the prior model. So now coming back on the 3 examples, let's try to start. I need the pointer here. Let's try. Okay, good. So first case, you have here the situation. So we have only 1 dice in hand here, and it can be either a 6, 1d6, or 1d12. So here we have the logic tree, very simple, 2 branches, and what is here is the calculating the probability to exceed a certain number. So very simple. For the d6, we will go until 6. For the d12, until 12. Here, equal prior weight, and so the updating has not yet started, and we will go quite fast from the first information, so the first throw we get here. So first result is indicated here, so it's 2. And then, since the first, of course, you're calculating the likelihood you have on the right side of the slide here. We calculate for each of the 2 branches the probability that we observed B, so 2 according to model 1 or to model 2. So for the model 1, the probability is 1 over 6, flat probability. It's just 1/6 because the dice has 6 faces. And here, the probability is 1/12. That's why that even after the first throw, we can have an update. And of course, if the result would have been 7 or 9, it would have been easy to conclude because 1 would have become 0. But for that, you will observe that, and I will continue. So with multiple set of throws. So the second is 5, and etc. etc. Each time, we will update. And we will, at the end of the process, and here is just after a 4 throw, we can observe that the probability that the dice would be 6 face is 0.96, and the probability that the dice would be 12 is 0.03. So this is a first very simple experience. And of course, if the dice would have been 12, we will observe that sooner and more sooner than later that we would have observed some result that would have excluded the other way. But this is very simple. Let's continue with the second example. And I will go a little bit quickly because you know already the process. So for this example, I should have 2 dice here, and due to my tool, I cannot only focus on 6 plus 6 or 4 plus 8. I just have to propagate some uncertainty. So there are 2 dices, and possibly 2 dice of 2 d6, but only 1 d4 and 1 d8. So it means that exploring all the combination, I have 7 branches that you can see here. And then same process again, my choice for this example was 2d6. So then we'll have the first throw that you can see that we observe 6. So the first 1d4 is excluded, of course. And then we'll see how it evolves. And you can see that due to the result, it's easy to exclude any branch that is not consistent, compatible with the results. But we never exclude any branch which is still compatible with the result. And we will observe that there is one branch that could be 8 plus 6, which will be this branch, will be never excluded. You will see that at the end of the process, the likelihood will decrease, but it will never be excluded. Then we will see progressively how it evolves. I think I went through, I'm just going fast because I think that I will elaborate the application to PSHA later on. And at the end of the process, which is almost done here, so after 14 throws, we can observe that, do not focus too much on this one, but between the two possible real solution or the possible solution of 6 plus 6 or 8 plus 4, but you can see here that I just plotted the 8 plus 4, but it's not the one I chose. And we can have, at the end of the process, the updated likelihood given here. So we can see that 6 plus 6 or 4 plus 8 are not so different from each other. However, all the other are are really considered as very low probability. So just my conclusion of that is that Bayesian updating process, especially for unknown or like hazard, the objective is not to try to find who is the real one, but especially to exclude or to give a very low weight to all the assumptions or the combination of assumptions that becomes very unlikely. So let me go first, last with my last example on dice, because I think it's coming, starting with a very interesting case of exploring hazard curve with a multiple strong uncertainty in the consideration, because here I have possibly 12 dice in hand, and the dice could be 1 to 3 or 0 to 3 d6, 0 to 3 d8, 0 to 3 d10, 0 to 3 d12, and 0 to 3 d20. And then, exploring all the situation, I have a logic tree with 1,000 branches. So the 1,000 branches are here, and we are just explaining or expressing the probability that from one dice throw we would exceed a given value. So it means that the maximum possible case may be up to 150, if I remember well. You can see that even at 10 to the minus 4, we are not reaching 150. So we are exploring a wide range of epistemic uncertainty, and each case is also associated with a random occurrence. Then I will follow this way, this time, how will evolve the confidence interval. So and at the end I will give you the real case I decided to use in this example. So first result. So you have here the result. Sorry, with my 38. So and this here is the likelihood of each single branch. So we have 1,000 branches, and each single branch likelihood has been updated considering P the B knowing AI. And here you have the range of the likelihood from the lowest to the top. And again, we will focus at the end of the one that we have been able to consider as very unlikely. So I'm just going now very fast. 2, 3, 4, etc., etc. You see that it's evolve a little bit, but you see how the quite stable evolution and how it helps to reduce the interval, the confidence interval. And at the end, I'm just explain the final step here. So you have here the arrangement I chose for this example. This is the point in the location or the likelihood. The real case was attributed due to the process, which also propagate the random occurrence. You have the likelihood here in this plot, and especially focusing on the amount of branches that have been considered as very unlikely. For sure, on this side, we have almost zero, or we have zero because it's not compatible with the possible arrangement. It's not possible for 1D4 to go 30 and more. But on this side, it's not zero. It seems to be zero, but it's only a very, very low value, but not zero. So we can rely on this result to attribute a likelihood consistent with the observation and all the process, epistemic and random process due to the observation. So let's come back now on the maybe a more let's say seismological case. So I will give now an example of an application of a practical PSHA case, full scope PSHA performed at a French national metropolitan territory scale. So the PSHA that was used in this case was the PSHA performed by Drouet et al. And published in 2020. So you have the reference here. Basically, there are, let's say, 4 main branches for the seismic source characterization models, 3 area source model, let's say usual one, and 1 smooth seismicity model. Then there were 4 GMPs that are illustrated here, and 100 random sets of A, B, and M max value that are also propagated in the in order at the end of the process to get from these 16 main branches to have 1,600 branches in total for the whole logic tree. Though you have just an illustration here, so we can get the 1,600 hazard curve for all the possible grid of the French metropolitan territory, and this is just an illustration that for the hazard curve or the hazard map that can be produced. But I will focus on the hazard curve from the example of Bayesian updating just after. So we perform an integral evaluation. So we assess the likelihood of the 1,600 curves. So it means that we did that for all the single branches of the logic tree. We use instrumental and historical observational data. For instrumental seismicity, it's quite simple. Just use an exceedance rate of a given PGA. In this example, we use 0.01G. We are in France metropolitan territory, so choosing a larger PGA would not be very informative. Then we also use historical seismicity. For that, we had to transform the PGA, the hazard curve in PGA to intensity through some relationship. You have the shape here. In a previous study, we use 8 different intensity to PGA relationship. We conclude that what is strongly important is to propagate the uncertainty, and for this we only use 2 different relationships, but propagating all the uncertainty and transforming step by step the acceleration, considering the probability that it would lead to an intensity from 6 to 9. And once this is done step by step, we just cumulate the occurrence rate of intensity to get an occurrence rate of intensity from 6 to 9. So this was the process. Then what we did, we cumulate rates from multiple stations. In this study, we use 20 sites. So meaning that we are just doing this, multiplying or summing all the occurrence rate or exceedance rate for acceleration multiplied by the time of observation of each station, and then we get an overall exceedance rate of PGA or occurrence rate of intensity. We apply and to perform the updating process, we use the Poisson approach, which is consistent with the assumption of the PSHA. We could take into consideration possible correlation with station, and if you are interested, there is one paper that we rely on to work on this study. Then we could also possibly account for any transposition from rock to soil, or even taking into consideration soil structure interaction if we would be in some situation. The way to do that is to make sure that we propagate all sources of uncertainty in the process. You have two references here if you are interested. Then in terms of results, you will have here the process, because for each type of observational data, it could be seismicity, sorry, it's in French, but it could be instrumental seismicity, it could be historical seismicity for intensity 6, 7, 8, and 9, and for each of the two relationships we use. So we perform the updating, and then we have a way to include this in an overall process. But let's focus first on the crude results, which is given here. We can see that we have all the 1,600 branches with the updated likelihood. And what I would like to point out here, you can see that depending on the type of data that has been used, the result is more or less efficient. And for instance, there is here a gray line which is almost horizontal. This is because it's because of this intensity 9. And when the process compare and applying Bayesian updating on this, for the French metropolitan territory and for intensity 9, the result is that all models predict zero observation, and the observation is zero. So no surprise, no update at all. And in another way to go through the results is to look at the original logic tree and to see how the branch can combine to each other. So I will not go into too much detail because I see that the time is running, but what we can do here is that we can have a look, for instance, and this is the smooth seismicity. So again, 1,600 branches, and the first 1/4 is smooth seismicity. Then we have seismic zone model number 1, model number 2, model number 3. Then we have GMP number 1, number 2, number 3, number 4. The same here, the same, and we have also GMP number 1, 2, 3, 4. So we can have a look and reconsider our choices, prior choices. For instance, what we observe that source zone model number 1, 2, and 3, I would say give almost identical results. So maybe this is not the appropriate way to propagate uncertainty. So we could think about a new way to remove two of them and to add a new way to propagate uncertainty on that, because we observe that comparing smooth seismicity and source zone model, there is a great difference. We can also assess some GMPs compared to each other and see if we consider that we have appropriately propagate uncertainty or not. So this kind of outcome is very useful, especially if this is done during the implementation of the PSHA. So let me now, and I think it may help a lot to invite actors of the PSHA to think and to reconsider their possible choices, or prior choices, or even belief. So now, let me go to conclusion now. I have a first slide with sharing some frequently asked questions, but I think I will prefer to get your feedback and your questions. So let me go quick to my conclusions. So I hope that I try to convince how important it is to evaluate PSHA results based on observation, and I would say the goal would be to improve confidence in achieving the CBR of the TDI. In this context, Bayesian approach are full of very useful provider of information. For multiple reasons, we can gather multiple type of observation, gather multiple sites, and invite actors to re-question themselves. In terms of perspective, we are going to continue to gather multiple types of observation, focusing especially on paleoseismicity. We have not yet used that in our context. For instance, it could be precarious rocks, it could be also karstic columns. So I would say no limitation. We have to do that, and we are going to work on that. Observed risk, there was some paper regarding how to use or the possible use of observed risk, meaning convolution of hazard and vulnerability. I would say so far, I've not found the appropriate process to do that. So not so, I would say there are still some limitation, no limitation for paleoseismicity. Then increasing the number of observation sites, no limitation. The objective would be to use all the possible sites, even if I did not mention too much, but due to correlation issues, we can demonstrate that for a given territory, we will achieve a kind of asymptote, and even if you add one site, the correlation will not help to improve or to get quantified additional information. But this helps not to make any subjective choice in the selection of station. And then be ready to evaluate or possibly update any new PSHA. And I would say it could be either during the PSHA or after, but I would strongly recommend to do this way during the PSHA, because it's a mine of useful information that can be provided to the actors of the PSHA. Thank you for your attention.
Any question?
We've been looking at this in California as well, and have found that a key issue is the conversion of the between the PGA to the intensity. In particular, the models that are used assume a simple relationship between them. And what happens is those relations work fine at the median ground motions, but seismic hazard gets driven by high epsilons, above the median. And if you take a PGA that's at epsilon of 1 or so above, you will overpredict the intensity by a 0.5 to 1 intensity unit. So that's a huge problem that you have to get out of the system before we can go back and recalibrate everything else. So those ground motion intensity equations that just use the intensity as a function of the PGA magnitude and distance, for example, have a huge bias for converting an above average or below average PGA. So you have to fix that part of the problem. That's what we're going back to now, trying to redo that conversion process. Because that was causing all of what looked like a huge discrepancy between what the seismic hazard is giving and what was observed historically by intensity. We're saying we're drastically over predicting the hazard, and we can explain almost all of that by the problems of the conversion of intensity to PGA for above average PGAs, which dominate your hazard at the lower return periods. Have you looked at that yet for France? Because I know I've talked to Gloria about this for a few times.
Thank you for your comment, and I would say that we have not explored too much. In the previous paper published in 2019, we explored 8 possible relations, but they had still the same shape and
they all have the same basic problem.
Yes, yes.
So this goes back, we found that 80 years, you know, Richter did this back in the 40s, so it's a problem.
But I was curious at the beginning because I was curious whether this, by propagating the uncertainty around the relationship, I was wondering if it would completely, how to say that, dilute or, I mean, the process, but it seems that it's still informative, so it means that we have to work on that, because I'm still convinced that it will be informative.
There's information here, clearly, but I think we have to get that correction done, because when you put in that variability, all the uncertainty, that actually tends to push you up to higher and higher hazard numbers as opposed to lower values.
Thank you. So we may work on this in Sigma 3, maybe.
Okay, thank you very much.
Thank you.
We have our last presentation. Graham Wetherill is presenting comparing seismic hazard models against instrumental data, theoretical and practical considerations.
Okay. So thank you very much, and thank you for sort of bearing with me to the last talk of the presentation. This is a general overview of work we've been doing in the Metis project, really looking at testing our experience in terms of I use the word testing, I'm going to use the word testing a lot, what I really mean is just comparison, making quantitative comparisons between seismic hazard models and instrumental ground motion data. It's quite useful going kind of at the last of the presentations, because several concepts that I'm going to introduce here you've already had very well discussed by earlier speakers. So there's some things I may sort of jump through a bit faster. So when we talk about how can we actually quantitatively compare probabilistic models against data, we've really got sort of 2 forms of observations. And again, this has been very well articulated early on. I consider these in terms of direct observations. These are measurements of engineering ground motion parameters recorded on instruments, which give an accurate representation of the shaking, but obviously suffer from the limitation of having a very short archive. On the other hand, we have indirect observations. So these are making inferences from non-instrumental observations, such as macroseismic intensity, and as we saw yesterday, from fragile geological structures. And these obviously can provide a much longer archive, from hundreds to thousands of years, but give an uncertain, sometimes very highly uncertain measure of ground motion. Important to also bear in mind with macroseismic intensity data, it is an aggregation of observations across an area, not necessarily a single observation. So I'm going to focus mostly on this idea of direct observation and what we can do with instrumental data. So you can go back in the literature to some of the earliest examples we have from how this is, or illustration of this. We have a paper from Ordaz and Reyes in 1999, who simply compared the rates of exceedance from hazard curves against the rates of exceedance of ground motions at a single station. Now you could look at this and say it's consistent. That's more or less what the authors themselves did, and I'd say that's a little bit questionable itself. But this is not a validation by any means. And one of the reasons for that, it's kind of an intuitive one, but there's you can illustrate this one very clearly, which is that there's a paper from Salim Boval and colleagues in 2008 that really demonstrated very clearly with a pretty simple experiment that you can do in a few minutes, that by simulating many sort of Poisson processes with a given rate of exceedance, a sort of a typical rate of exceedance we use for ground motion simulations, you would need about tens of thousands of years of observations at a single site to be able to get an estimate within a reasonable range of the long-term rate of exceedance. So in terms of whether or not we can use instrumental data to compare or to somehow validate seismic hazard curves at a single site, we obviously can't do that. But If we consider many sites and many probabilities of exceedance across many locations, we can begin to aggregate these observations. And the advantage we have is that by doing so, we can gain some statistical significance, so we can get more, maybe make more information and more inferences in a shorter period of time, but we're obviously going to lose any sort of spatial precision and resolution. Realistically, when you come to this at the end, you can only really say model A or model B is perhaps comparing better or not quite so well for a country or a part of a country, but not necessarily a locality. And even to do this, we need actually to gather data from many sites, particularly if you're working in areas of low to moderate seismicity. And to do this, as we've been trying to do here in France, we're also doing the same things in Switzerland, Germany, and Italy. We need to gather data from not just our standard strong motion networks, we need to pull together all the data, all the ground motion observation data that we can get our hands on. And so we're going to be combining both strong motion and weak motion broadband velocity data. And the way we can do this is through through IDA, the European Integrated Data Archive. This is a federation of data centers that archive waveform data and metadata. It has access to this data through standard APIs, which make it actually possible to very easily sort of algorithmically download and retrieve large numbers of data. And it has standardized formats for strong and motion and weak motion data, which means it's possible to pull in really all the data that we can do. And this was really our starting point, was to create an archive of ground motions from IDA. So we created a ground motion database, more or less covering the region that you see here. So mostly focusing on France, Switzerland, Germany, and I'd say northern Italy more than the entirety of Italy. And we set our sort of search criteria for 21 years, so going from 2000 to the end of 2020. We include data from IDA and IRIS, and we include all four both strong motion channels and weak motion channels, and we also include both permanent and temporary deployments. This is obviously an automatic process, so it's not necessarily verified by inspection, but we do have various numbers after quite a long processing chain. We also have various sorts of quality criteria that we use to sort of try and throw out various records. And at the end of all of this, we end up with about 82,000 pairs of horizontal earthquake spectra from about 1,800 events and nearly just over 2,800 stations. And this has all been done using a software that was developed by my colleagues at GFZ called Stream to Segment, to be able to sort of pull in or download and process massive volumes of ground motion data from open archives. So this is potentially a very useful database, particularly if you're looking at ground motion model development. But if we want to use it for any sorts of comparison or quantitative comparison purposes, we need to have a degree of confidence that the data we've got is an accurate or a faithful representation of what's actually gone on in the time period we're looking at. And this is where we encounter what I've said to be the biggest practical challenge in all of this, which is something that I've colourfully called the leaky data pipeline, but really it's just completeness. Because in the ideal case, in the ideal world, we have an earthquake occurs in a relatively well-instrumented region, and the waveforms, the waves shake the sites. This triggers the sensors themselves. They produce digital waveforms. These are archived by the local network and then gradually made available to online services. And from there, we can basically download, reprocess them, and we produce an entry in a flat file, so a simple parametric table, one sort of row per record. But the reality is this isn't how it really goes, because we have cases, in any earthquake, we'll have cases where the sensors are offline, where the sensors maybe don't trigger, it's a noisy environment, there's mechanical failure, maybe it's just an unusually weak motion. We have cases where the records are discarded by the local network, maybe it's known instrument problems, other issues of noise, or there can be timing errors in the instrumentation that means that they're not correctly associated to the right events. And then there's also the question of how much data the networks make available to the archive, so they may not make it available, it may be restricted. It might have been that at the time we downloaded the data, certain data sources were offline, or maybe they provided incorrect metadata, which means we didn't pick this up correctly when we did our search. And finally, even if we've got all these records and we download all these records, it's not that we can retrieve ground motion parameters for absolutely every single record. There's always going to be a proportion of these records that are effectively garbage, where you have clip signals, poor signal to noise ratio, incorrect responses, or just plain outliers. So in this process, we are losing a large amount of our data. So even though we've created a pretty large database of ground motions, this is not a faithful archive. of what's really happened at our sites. And this is important if we're going to use this to make any quantitative comparisons against ground motion data. So how can we still compensate for this, or what can we do with this? Well, there are several options. We could simply say, well, I'm going to limit just my comparisons to the few stations that I know have the longest operation or sort of best performance, which is great, but you're going to throw out quite a lot of your data or a lot of observations when you're doing it. You could just simply renormalize your observation windows. So IDA is very good in terms of having a lot of metadata information that tells you when stations have been offline. So you could say, well, okay, I've actually only got 3 years of data rather than 5 years, and renormalize. But that is useful, but it doesn't necessarily cover all the different ways in which you're going to lose data. You have many cases where the station's online, but we just didn't get data for that earthquake. So what we've done here is basically to kind of fill in the gaps through a different way. Because when we have shaking that's not observed at a site, but we would expect to have seen it from the earthquake and the location, we can define an amplitude of expected ground motion and its uncertainty coming from a ground motion model. We're not the first people to do this. This has been done in a few previous studies. And this is something you might consider to be like data imputation by regression, using models or based on observed data to sort of fill in the gaps for the missing data. And to do this, you need a harmonized earthquake catalog, so you need some sort of reference that tells you the truth, let's say, in inverted commas, an appropriate ground motion model, and of course, when we talk about observations now, we don't have a single observation, we have a probability distribution. So we've got uncertainty, and this uncertainty has to be propagated into these comparisons. Now, although we don't have a complete archive, we still have a lot of data. And we can actually do something a little bit better than just taking a ground motion model from a paper and just throwing it in and hoping for the best, which is that we can use the data that we do have to retrieve between event and site-to-site residual terms. So, for example, on the left here, I have one earthquake. It's in southwestern Italy. These are all the stations that may have recorded it. I don't know why some weren't there. But the fact is, even though I didn't have every possible station recording the earthquake, I have a lot of them. I have 72 records. On the same time, on the right-hand side, I have a station where I have many earthquakes recorded, but I don't necessarily have all of the earthquakes that could have influenced the station. And so from these, I can retrieve my between event and site-to-site residuals for many stations. And with this, I can actually reduce this uncertainty in the data that I'm filling in. I'm no longer filling it in with the ergodic sigma. I can actually remove parts of this and have a much narrower uncertainty when I have good observations for a station or for an earthquake. So this ends up being my processing chain that I would sort of start off with a harmonized earthquake catalog. I can configure this to make sure that I'm selecting magnitudes and station distances that are compatible with my seismic hazard model. So I'm trying to compare like with like as best as I can. And then for each earthquake in the catalog, and then for each station that's of interest, I would use my model to calculate acceleration. And if I have observed ground motion, that's fine. I take that, I put that into my archive, and I have no uncertainty. Otherwise, if I don't have this, I would look to see if the event has a between event term. If so, I add this to it and take out that part of the variability. Same with the station term. And in the end, what I'll produce, and this is what I would sort of classify as being data imputation by mixed effects regression, what I produce is an observation history. So this is a pseudo-history for a station that contains a mixture of observations and hopefully a proportion of calibrated predicted distributions. The exact proportion of this is obviously going to depend on site to site. I might have stations where I have mostly observations and a few gaps filled, or else I have stations where I have, particularly if I'm using temporary deployments, where maybe I only have actually a couple of years of data, but I can sort of fill in the rest. So it should be compatible with the hazard model conditions. This is something that can be built into the process. And something that's particularly useful, and you're going to see why, is that what we actually do here is we actually normalize our station histories to the same time period, regardless of the actual duration of operation. And this actually pays off for reasons you're going to see in a few slides' time. So this is the kind of where our starting point is. We have our ground motion data. We have these sort of pseudo-histories. So what I need now is my seismic hazard models. And in these examples here, I'm comparing two seismic hazard models that cover metropolitan France. One, which you saw in the previous presentation by Drouet and colleagues in 2020. But I also have available to me the 2020 European seismic hazard model. I won't go into details on all the background of all of this, but we needed to create a harmonized earthquake catalog. We did this by harmonizing seismicities from various local, national, and ISC bulletins in the region. And I need to do a sort of extensive amount of ground motion residual analysis. I need to work out which GMPE or which GMPEs would be most suitable for this purpose. And it turns out that for both strong motion and weak motion records, actually, the Abrahamson et al. 2014 NGOS2 GMPE and the ESHN20 GMPE work pretty well for most cases in Europe. So, okay, I've got my models, I've got my data, but how do I actually do these comparisons? Well, as I said before, what we're actually doing here is to aggregate many observations over many sites. So we need to create aggregated seismic hazard curves, so aggregated curves of observation and aggregated curves of expected or seismic hazard. So this actually can be done in one of four ways, and it's done in a paper by Mack and Schorlemer in 2016. Really, it sets out and articulates very clearly the four different ways we can actually aggregate seismic hazard curves. And depending on which way you actually aggregate this, you may be handling different probability distributions or different statistics. And I'm going to just try and go briefly through them. I'm going to work mostly with one type, but I'm going to just give a quick overview. So I consider here my case for France. I have 357 stations, both strong and weak motion. So consider I have S independent, I'm definitely going to come back to that point in a little while, independent sites and a probability of exceedance in a duration we're interested in, which in this case was 21 years. So the first way I could aggregate my seismic hazard curves, and which is more or less what you saw from Emmanuel in the previous presentation, would be to simply sum up the numbers of exceedances from all of the different stations within a given within my time period of observation. In this case, okay, that's where it is. In this case, my observed hazard is simply the sum of the total of the exceedances of a given fixed level of ground motion, so 0.01 G, 0.2 G, and so on. And my expected hazard is simply the sum of the expected rates from each of my stations. And because we're dealing with Poisson variables, then the aggregated seismic hazard curve has a Poisson distribution. Alternatively, instead of looking at the total numbers of exceedances across all the stations, we can look at our seismic hazard in terms of the total number of stations with one or more exceedance of a given ground motion level. So in this case, our observed seismic hazard curve is simply the numbers of sites with one or more exceedance, and my expected hazard in this case is a sum of Bernoulli trials, so Bernoulli trials with heterogeneous probabilities. So this is basically means that we actually have to deal with this with the Poisson binomial distribution, which makes life a little bit more complicated. It doesn't have a nice, neat, closed-form solutions for many things, but it's another way we can look at it. Alternatively, rather than setting fixed thresholds of acceleration, we can determine our aggregated hazard curves in terms of the number of exceedances of ground motion corresponding to a given return period or given rate of exceedance at each site. So rather than having a fixed ground motion level, the ground motion level is actually dependent on the site, and because it's dependent on the rate of exceedance, our observed hazard curves start to become themselves model dependent. The model is setting the threshold of the exceedance. Well, and this is why now when we look at our seismic hazard plots, we have the total number of exceedances, probability of exceedance, and my observations, which are the black line, now have a distribution. These are model dependent. And again, these are Poisson variables because we have a fixed rate and a different observation window for each station. So we're dealing with a Poisson distribution. The last form, and this is the form that I'm actually going to use for really the rest of this presentation, is the last of the four permutations, which is to consider not necessarily the total numbers of exceedances, but the number of stations exceeding their corresponding rate of acceleration with a given rate of exceedance in a given time period. In this case, then, our observations, once again, are model dependent. This is set by the numbers of stations that would exceed their threshold will obviously depend on the threshold, so it depends on the model, while the expected numbers of exceedances actually end up being quite simple. It means that our expected number of exceedances can be modeled by a binomial distribution if TS were constant, so if my durations were constant, or they can be Poisson binomial if they're not. But fortunately in our case, because we've used this data imputation process and we've normalized all of our observations to our stations to the same observation window, then we've actually made our our process homogeneous, so we can actually use a binomial distribution. This is exactly what we do. So this is just to sort of familiarize you with the curves that show these comparisons here. What this really means is that I have in my plot here my seismic hazard observations. These are red curves for different quantiles and blue for the mean hazard. And this is the total numbers of sites exceeding the threshold acceleration. So these are model dependent, while the black line and its shaded grey region are the mean and the 5th to 95th percentiles coming from a binomial distribution. And we say in this case, because we've set our common duration for all of our sites, it is a simple binomial distribution. It's dependent purely on the numbers of sites and the probability. So to interpret these curves, generally we would say if our hazard model is overestimating the spectral observations, so we're getting higher hazard than the observations are bearing out, then our curves should fall below, our hazard curves fall below the black line. So this would suggest that the best agreement is somewhere between the median and the 16th percentile. Important not to lose sight of the fact that we're still dealing with short periods of time, so the engineering significance is really only achieved in this sort of lower region of the curve. For higher regions up, we're dealing with probabilities that are too high, really, for most common uses of seismic hazard. I made the assumption early on about independent sites. This is really something that's very difficult to ensure. And previous studies on this topic have tried to do this in one of two ways. Either they've been selecting their sites with a given minimum spacing between them to try and make them as independent as possible, or they just select some sites around and cross their fingers and hope that that was probably independent. What we've done here is to use a minimum spacing of 30 kilometers. So what I'm actually doing is not necessarily selecting all of my stations. I'm going to try and space my stations out, so with a minimum spacing of 30 kilometers, which reduces my number of observations from 357 to 115. I said early on we're dealing with uncertain observations now because we're using ground motion models to predict or fill in the gaps. We have some observations with no uncertainty and other observations with uncertainty. And so while we've often considered exceedance to be a binary state, it either exceeds or it doesn't, now we have to deal with the fact we're dealing with a probability distribution. Once again, Mack and Schorleman propose a relatively clean solution for this, which is that our stations are the sum of the probabilities of 1 minus not exceeding the station from any earthquake. So this is something that can be dealt with quite easily, and this framework could also mean that you can use indirect observations as well. So macroseismic intensity could work here. I'm not going to show it, but it could work in this same framework. So that's my general sort of setup. Now, what do the results look like? Well, I have here my two models, and if you recall from my explanations, then if my hazard curves, if my curve dependent or my sort of model dependent curves are below this black line, then it would sort of suggest that my hazard is overestimating with the spectral observation. So this plot on the left here would suggest that the lower quantile, so the sort of around somewhere between the 5th and 16th percentile, is coming into best agreement with the observations. And this is the left hand was the model of Drury and colleagues. On the right, maybe you could say the picture's a little bit better. For the probability of exceedance that I'm perhaps most interested in, I could actually say that the median and gradually towards the mean is getting into better agreement with the observations that I've been seeing. So in Drury et al., the observations align slightly more closely with the lower quantiles. For the ESHM20, it's lining with the median. So in any sort of conventional sort of hypothesis test, neither of these models would really be rejected. So this wouldn't be a simple binary, one is better than the other. But you might lean towards this and say, well, okay, perhaps then in this case, I would prefer the ESHM20. Is this the end of the story? Well, not really. Because the center of even just focusing now on the ESHM20, and from now on I will focus just on the ESHM20, although perhaps you could argue that the model is becoming a bit more consistent, so we do have observations that are sort of aligning or perhaps agreeing a little bit better with the center of the distribution. Overall, it would still suggest that perhaps our seismic hazard model is somewhat or slightly overestimating compared to observations. And potentially even then, our model is a little bit too conservative. And the ESHM20 was a particularly useful model to test this out because unlike the other previous models in our region, we have a backbone ground motion logic tree. In fact, we have backbones in several parts of the model. But our backbone ground motion model logic tree is calibrating the epistemic uncertainty on the GMPE according to, it's calibrated both on terms of region-to-region variability in source stress parameter and region-to-region variability in attenuation. And of the two, the source stress parameter is dominant. Now, in the way we implemented this, we actually did regionalize the attenuation. So the attenuation is sort of calibrated for different regions of Europe. But I didn't do this for the source parameter regionalization. And that's, I won't go into details, and I'm happy to explain offline why I didn't do that. But when I looked at the actual ground motion data itself for France, the ground motion data did more or less suggest that for regions where I have good observations, it would tend towards a slightly higher tau L2L, a slightly higher delta L2L. It would tend towards a slightly higher stress, a slightly higher than expected, or higher than ground motion systematically than the European average, and it would tend towards slower attenuation. And given that I know that the tau L2L variability was the most dominant, what this really suggests is that my ground motion data is saying more or less I would expect that it would be the higher branches or the slightly above average branches that should be in better agreement, whereas when I test against hazard, that's not the case. It seems to suggest that it would actually prefer or be a little bit skewed towards the lower branches. And this is where we come back to the problem of ergodicity and the ergodic continuum. Now, I won't go back into detail. Again, a fantastic presentation yesterday from Norm Abrahamsen made this all, I think, hopefully very clear. But what we really see is that when we've been running these seismic hazard models, both for Joy for France and ESHM20, we've been running these with ergodic ground motion models. We've been using the full sigma. But obviously in places where we have repeated observations, so tau L2L, path to path, and site to site, our real distribution of ground motions at a site is not ergodic. It is truly a non-ergodic ground motion model. Yet virtually all the regional PSHAs that we're using use ergodic ground motion models. But the ESHM20 ground motion model is very useful because it was actually itself a partially non-ergodic GMPE when it was developed originally. So we have our standard ground motion model, our standard between event and within event terms, and we have our site-to-site terms, but we also had recalibrated this source region to source region and delta C3, which is not directly analogous to path, but it's picking up some of the same phenomena. And when we implemented this, we moved our source-to-source and path-to-path variability out of the sigma and put it into our logic tree. And what we're left with was simply our source region corrected between event, our site corrected within event, and our delta S2S variability. And if we have many observations at the stations, which we do have now in our data set, we could perhaps put a first order estimate on delta S2S and remove or certainly significantly reduce the phi S2S term. So it means what I can do is I can conduct an experiment where I'm going to compare three different forms of the model. I can start off by comparing my ergodic PSHA, exactly as it's come from out of ESHM20. I can compare a partially ergodic form of the model, one in which I've removed the site-to-site variability because I've calculated delta S2S for the vast majority of the sites which I've been able to consider. And in the third form, which I'll consider, which is actually, again, a suggestion I got from Norm Abrahamsen about a year and a half ago I presented an early form of this presentation in Avignon, which would be to say, just hypothetically speaking, although I don't necessarily have a fully non-ergodic ground motion model GMPE implemented that I can use, to simply say what might be the implications if I used a sigma term that was representing the best reduction I could achieve in sigma with a fully non-ergodic model. And for this purpose, I'm using a model that was calibrated by Nico Kuhn for Italy, which gives sort of a fully non-ergodic sigma of around 0.35. So this is perhaps considering the best case, but otherwise everything else is kept the same as the partially non-ergodic case. And what we can see is as we go from ergodic to partially non-ergodic to, let's call it equivalent non-ergodic, we go from our curve starting to favor a little bit below the mean, so starting to favor the 50th percentile, to then aligning much more clearly with the mean. And then when I go to fully non-ergodic, it almost overshoots and seems to actually prefer branches that are a little bit higher than the mean, which is kind of what I was expecting from the underlying ground motion data. And just for completeness, we also did the same thing for the Drury et al. Model. I couldn't really get a partially non-ergodic form of it, but you see the same approach. When I basically reduce the sigma, we go from the model favouring the lower quantiles, the sort of 16th and 5th percentile, to then getting to much closer alignment with the centre of the distribution. Now, why is changing to a non-ergodic actually changed here? Well, this is something that, again, Norm kind of articulated yesterday, except I would go and say, while it's true that on a site-by-site level, you will have some, you can't guarantee that going to non-ergodic will reduce your seismic hazard. When you're aggregating over hundreds of sites, overall, you will see a tendency towards reduction. And why does this happen? Well, if we just think just very basic level about what our curves are doing, if I add on a delta S2S term, a simple linear term, without adapting sigma, I'm simply going to be moving my hazard curve up or down, left or right. Whereas if I change sigma, I will either steepen the curve if I've reduced sigma, or I'll flatten the curve if I've increased it. And when I consider several hundred stations all at the same time, clearly some of my curves are going to shift to the left, some of my curves are going to shift to the right, maybe in even proportion, maybe not, but they will all steepen. So overall, my aggregated seismic hazard curve is going to lower for switching to a partially non-ergodic or a fully non-ergodic process. Now, of course, as we've discussed yesterday, this doesn't mean this uncertainty is just disappearing. It should be going into the epistemic uncertainty in the quantiles. But I'm not actually going to cover that for this point in time. So what implications does this have for testing? Well, firstly, this is not a new observation. This is really going back many years, and it's been the motivation for non-ergodic seismic hazard for a long time. But this is the first time that I have seen where we can look at a much shorter period of instrumental data and still come to the same conclusion that it's necessary in order to be able to get a better match, a better agreement between hazard and observation, we need to move to non-ergodic models. This does have implications if you're going to use testing or these comparisons in any way to prune or to reweight the branches, either just to remove them or if you're looking at the Bayesian updating approach, which is to say that if you're going to test ergodic seismic hazard observations, which are almost always non-ergodic in regional models, these are going to give you the impression that hazard is systematically overestimated with respect to your observations. And this might mean that your Bayesian or your other processes are going to give higher weight to the lower quantiles, which can end up, as we've seen here, being actually in contradiction to what your underlying data is telling you. It's simply because you've been comparing ergodic versus an ergodic model versus a non-ergodic process. We also would point out from experience here that in some cases, particularly now that our models are becoming more backbone-like, ESHM20 had a backbone in the activity rate model and backbones in the ground motion model, is that sometimes these uncertainties trade off, that you can have, for example, a branch which has a combination of a very high activity rate with a very low ground motion stress drop. Now, each of these would be unlikely branches. They would be sort of given low weights in their underlying models, but you might find that because of this trade-off, they actually end up being agreeing quite well with the centre of the distribution. So it might be given a higher weight over slightly more likely combinations. So these are the general implications. But I've got a few minutes left, and I want to talk about the last sort of topic, which I've alluded to, but haven't really come to a conclusion on, which is this issue of spatial correlation and spatial dependence. So far, the aggregated seismic hazard curves have needed, because of the probability distributions that we're using here, have needed to assume independence between the sites. And I tried to achieve this by putting a gap of 30 kilometers between the sites. But for France, this removed, well, 2/3 of my stations, so I'm already removing a lot of data. And 30 kilometers is arbitrary. I didn't really have a good explanation. I could go to a larger gap and remove more data. I could go to a smaller gap, keep more data. I couldn't really necessarily be totally sure I had independence. So how can we get beyond this? How can we avoid this assumption? Well, firstly, you need to understand where does this come from, and it really comes from two places. We have, when you have a large earthquake, we're very likely to have multiple exceedances of ground motion from the same site, and that's as true in your seismic hazard model as it is in your real-world observations. And we have spatial correlation in the ground motion model residuals. So our probabilities of exceeding ground motion given a particular scenario are conditionally dependent if your sites are nearby. And one of the things we can do very easily, because we've been using the OpenQuake engine, is that OpenQuake has a very fantastic feature in terms of being able to allow you to run your seismic hazard either in the conventional, say, classical PSHA approach, or to run it by what we call a Monte Carlo or event-based PSHA approach, by basically generating thousands of realizations of seismicity so basic realizations of ground motion at the sites. And with the event-based approach, we can actually take our same seismic hazard models and we can run these, and we can actually put in spatial correlation and spatial cross-correlation into the seismic hazard model. So I did. So I've got the same model, the ESHM20, and now I'm using all of my sites, so not just my 115 sites, I'm using all 357 sites. Including more sites is narrowing the confidence intervals, so I have a slightly narrower distribution here. But when I introduce spatial correlation, it doesn't change the picture, really, to any extent. Now, for France, this would suggest the influence of spatial correlation is negligible. That's not necessarily generalizable. This is a low seismicity region. You have a very uneven network distribution. And this assumption or this result is going to be network topology specific. So it depends on how well spaced your stations are. So it might be more significant elsewhere, or it might not. But probably, and it took me a little while to get to this realization, it doesn't make any sense to be looking at this from the hazard model side. We need to look at our statistics of what we're doing when we do our comparisons. Because when we're dealing with stations that are nearby one another, or stations where you have exceedances that are potentially associated, then this assumption of independent identically distributed processes is no longer true. So if we start off with our simple, in this case, a simple binomial assumption, where we just have our total numbers of sites and our probability, we have our binomial distribution has a given mean and standard deviation. But if our trials are associated, if this Bernoulli processes are associated so that you can't necessarily say that exceedance at one site is conditionally independent of exceedance at another site, we have overdispersion in this process. So this is no longer a simple binomial distribution. We now have a larger increased sigma. And this has been suggested by several authors and quite well articulated by Alvarello and Peruzza in 2017, who sort of showed that you would need to modify your standard deviation, so your second moment of your model, to account for this association. So we can do this in various different ways, and what I'm actually going to do here is show that we've been looking at various forms of over-dispersed binomial distributions. So if we consider that we have a certain numbers of sites, if our hazard is given in terms of a certain number of sites out of our total number that exceed the ground motion level for a given probability of exceedance in t years, I could parameterize this via a beta binomial distribution, a negative binomial distribution, or the one that I'm going to focus on here, which is a distribution called Conway-Maxwell binomial. In any of these cases, we're adding in a new parameter. We're going from a 2-parameter to a 3-parameter distribution, where this new parameter is trying to account for this association. I'm using the word association rather than correlation in this case. We're not dealing with Gaussian processes here. So the Conway-Maxwell binomial has a nice property, which is it has this additional term nu, which takes the value of 1. If it's 1, it basically collapses back to a binomial distribution. But it's a measure of the degree of association between Bernoulli processes, between Bernoulli trials. And these parameters, alpha and beta, or p and nu in our case, they are always going to be region dependent because they're dependent on the site typology and the network topology and the seismicity distribution. You can't necessarily know what these parameters are, which means we have to try and get them from somewhere. And one of the things we can do is to go back to my stochastic event sets and my ground motion realizations, and from my ground motion, synthesized ground motion histories, I can fit these distributions to different branches of the model. So I take my ESHM20 model, each one of its branches, I generate my stochastic event-based PSHA, 500 realizations of 20 or 21 years, including spatial correlation, keep all of my sites. And we can see here, if I fit, this is just the realizations for a single branch, so how many sites exceed their ground motions in a given 20-year period. We can see I have fit a simple binomial distribution. Again, it's come from one probability and my total numbers of sites. And I've fit the 3 alternative forms, beta, negative, and Conway-Maxwell. And from the AIC, we really see that it doesn't really matter which of these other distributions you use. All 3 of them show similar fit to event-based exceedances. In the Conway-Maxwell case, it has a new term, sort of 0.05 to 0.1, so it has really strong positive association between exceedances at the sites. So this overdispersion is evident and it's significant. How does this vary? These parameters vary with branch. There is actually some variation across the branches. Some of this might be reduced if I were to run longer event sets. And when I try to look into what's explaining this variability, it doesn't correlate obviously with any particular trend in the branches, which took me by surprise. But what it does mean is that with these estimates of nu and p coming from our common Maxwell distribution, we can then repeat this observation now using an over-dispersed model rather than a binomial model. And what this really does here, or the main impact from this, is that this massively increases our confidence intervals. And in fact, our sort of mean, or sort of our expected distribution is more or less the same. But by using this over dispersion, we have a much, much larger range of numbers of exceedances that would be consistent with the underlying observations or the seismic hazard models. So including spatial correlation or moving away from a simple binomial model to some sort of correlated or associated binomial model isn't necessarily going to change the overall trend in this case. Well, most of the model fits perfectly well with observations, or is within the quantiles, but we do significantly increase the confidence interval. So basically more of your models, more of your branches are likely to be consistent with results. So I'll finish now with just a couple of thoughts and a couple of points on this, which is coming really from my experience of working on this now for a few years. One of the main problems I've found looking at various sort of papers in the literature on this question of PSHA testing is that there's not a lot of reproducibility in the testing process. For the seismic hazard modelers ourselves, we've now had several decades, at least 15 years, of doing a lot of work on verification, a lot of work on validating PSHA software, on model checking, model consistency. Yet of the papers that I've read on testing, not one single paper was reproducible. Not one single paper on testing explained their full data set, showed how they were dealing with these issues of completeness, or provided any sort of code that was in any way allowed me to reproduce their results. So it doesn't make sense that we continue with the seismic hazard model community being rigorous and open on one side and the testing community perhaps not following suit. That's a little bit of complaining I have here. The utility of all of this, despite the amount of work, I still think the utility of this sort of testing against instrumental data is really still quite limited. And the most achievable purpose is consistency checking. This is never going to be really a true independent validation. So it's something that shouldn't really be applied, and I think Emmanuel made the point earlier, and I completely agree with it. This is not something that should be done a posteriori. We shouldn't be just developing models, putting them out there, and hoping that someone comes along and tests this and comes back and tells us, good, bad, well done, you need to go back to check your assumptions. It's something that should be iterative. It should be in the model development process. But this needs to be, for this to work, this needs to be low cost. Because if it's going to take you years or months of work to get data to be able to do this, your modelers are not going to do it. So, and when you do this, we also need to utilize data that's being used for the model development, whether it's harmonized catalogs, ground motion, flat files. We need more data to do these sorts of things. We are getting it, but we also need to be aware of these limitations because of these issues of completeness. Even though we have amazing recording networks, we have lots of gaps and lots of holes. And our macroscopic observations could also be incorporated, but these same issues of incompleteness apply. In fact, if anything, I think that gets a little bit more complex. One last point to make as I finish, as a bit of advertising from something we've done in Metis, is to address the point I previously complained about openness. We developed all of these things into an open source Python toolkit for this purpose of quantitative comparison of hazard models against observational data. And so not everything that I've presented here is already in the toolkit, but the vast majority of what I've shown here is in this toolkit that you can download, it's free to use, it's accessible, it's interoperable with OpenQuake, with PyCSEP. It can do testing not only in terms of, or comparisons not only in terms of hazard curves, but also in terms of source models, ground motion model residuals. There's a few more features to come along before I finish the work, but this is one of our main deliverables from Metis. The testing toolkit, if you download it, it does have API documentation. I'm still finding a host, but I think I'm getting there. And it will start to have, we have a Metis deliverable on this tool, and there are Jupyter notebooks and demonstrations on their way. So one of the things that we are trying to come away from all of this is that everything that I've done, everything I've shown here, will eventually be something that you can reproduce, and you can download these toolkits. You can use easily. Not one thing that I've done here or used here has used closed or proprietary data. Even everything from the data, the models, this is all now completely open, and the code is also open as well. So I'll just say thank you, and the deliverable is being finalized, and there's more information, including a webinar online that you can find through the LinkedIn website or the LinkedIn feed for Metis. Thank you.
Thank you, Graham. Any question?
Thank you, Graham. It's a very impressive work, and I really congratulate with you. And I'm a bit embarrassed because my question is actually very simple, but maybe I missed that. Two things. One, I suppose that you are using the same, so earthquakes in the same range of the hazard model, right? So above the minimum magnitude. Yeah. And the second thing is that, well, and that's, so the hazard model is the clustered, whereas are you in any way, let's say, considering that in the selection of the events that you are using for the testing?
Yes, yeah. So this is completely configurable. Yes, everything I've done has been working from a declustered catalog. I didn't have exactly the same clustering algorithm from the Doriator model, and I think I don't know if I have it exactly right from ESHM20 either. But overall, it was a declustered catalog. And when you run this in the toolkit, you can choose to do this. So you can run any declustering algorithm you like. You can get these outputs, and this can be plugged in. So that was one of these objectives of this imputation process, is that you want to be able to really select your sites and your magnitudes that are as consistent with your hazard model as you can possibly make it.
The ground motion model you choose to fulfill the gaps in your observation dataset will impact the test results?
You would think it would impact quite a lot. I mean, so I went through basically a two-step process in this thing, which is to say I looked at a whole various range of ground motion models for Europe, and I looked in detail at the residual distributions, and in the end you come down to really only a handful of models that I think don't really have obvious biases in terms of between event or within event variability. Within those models that I did look at, whether it's ESHM20, whether it's Abrahamson at all, actually the impact is not so large. So when I would say if you're quite rigorous in how you select your model, and perfectly reasonable to say to do this with different models. But another reason for using the toolkit is to make this really easy. This is one Jupyter notebook you can do this in now, and you can configure models so you can say, what happens if I switch this to GMP? It takes a minute, nothing more. You can use different models and you'll probably come to the same sorts of conclusions. Of course, the impact will also depend. I'm doing this in Italy as well. In Italy, we have a higher number of observations compared to France. So the more we actually can anchor our models, the less sensitive it becomes to the choice of model.
When I worry about evaluating ground motion models, I don't pay attention to how well it fits data. I pay attention to how well it extrapolates to the scenarios that are going to control the hazard. And so the question here is, on the part of the hazard, are you testing, if I had, let's say, ground motion models that worked really well at magnitude 4s, or is 4 your minimum magnitude you're using for these calculations?
4.5.
4.5. So let's say it was working really well for 4.5 to 5.5 at 50 to 200 kilometers, right, where this probably the bulk of your data are. Yeah. But does that really help us for evaluating the seismic hazard from magnitude 6s at 10 to 20 kilometers, which is going to drive our actual design values?
Yeah, my answer to that one, of course, on a conceptually, no, but I'm not necessarily selecting these models for the purpose of running PSHA. I'm selecting them for filling in the gaps. So in a way, what I want to check is that they are working adequately in the range of the data that I have.
But when the test that you're doing is on hazard results,
yes.
Right? And the hazard results that you have to check is on a shorter time period. That's all you've got, right? I mean, so I don't have a solution, but I think we need to be careful about if we get consistency or inconsistency for these scenarios that control the, let's say, hazard over 30 or 50-year return periods, does that really inform us about how well the model is going to be working at our 1,000-year return periods, right? That's a fundamental question that we always have on this.
And I would say generally, no, it doesn't. This is where you would need to turn to fragile geological structures or other
intensity
forms.
data or something else.
I mean, no, it's this is why I say I still believe this has limited utility here. It's not necessarily going to address all of our questions, but it can potentially give us a little bit of insight if we take into consideration all these factors. So in that sense, and I think I deleted a point about how it tests or how you can, if you can use this to verify or prune outlier quantiles, because my general view on that is no, you can't. You are not going to have enough data to really determine that you can reject your outliers. So this is more in terms of it's a first order check. It's a first order sanity check, which is why I say this is something that should be within the model. But I would be very cautious about seeing any results like this. And unfortunately, I haven't found too many cases. I haven't found in any results anything that makes me say my hazard model is wrong. Maybe I'm a modeler more than a testing person, so maybe I'm just being very generous on myself, and I'm not.
There's no huge discrepancy. Is what you're saying.
Nothing from any of the results I've seen, which is quite surprising, has made me think we need to go back and we need to recheck an assumption. We need to do something else. So it's more about just checking or giving that first level of consistency, because at the very least, our observation window should be, let's say, a feasible and not too unlikely realization of what our model is telling us. And that's really as far as we can go with this. It's not necessarily going to give us anything that we can do to sort of say anything about the large magnitudes, the short distances. This is well beyond what this data can do. Maybe in slightly higher seismicity regions with more records from large earthquakes, you might be able to make an implication, but even then I would approach it with a lot of caution. So no, it's a first order check. It's something that I think modelers should be able to simply point to, say, we did this, it's where we are, but it's not, nothing that I've ever seen in any of this was maybe say, yeah, Stefan Drury and colleagues, they need to really do this, or we need to rethink everything in ESHM20. Nothing has told me that so far.
Can I add something? Again, I'll be a little bit shaky with my voice probably after 10 years of not speaking in the public. But, well, actually, there could be a case that you could check if you are well doing with the instrument location. Meaning, from your hazard map, you can deaggregate what is actually eventually affecting there, with what type of magnitude and what type of distance of the location. Then you can actually understand if your first order check is good with that instrument event recording. Yeah. This is a way of maybe checking.
Yeah, I mean, these are open source tools, so I will take suggestions and I will take contributions, any of these things, and there's a lot of things that you could do from this.
For me, it's more like a comment rather than a question. I see all these validation and testing of the models more like rejection criteria, because as Norm was saying, probably you can just test against data that you already have. So if they don't match the data, then you can reject them. But you don't necessarily be able to say, okay, it works fine for all the magnitude and distance of interest. So it's like the presentation yesterday about the rocking, the balance rocks. You can compare to data and reject those branches that doesn't match the data because they are unrealistic. But in reality, you cannot just validate or justify the ones that you have at the end.
Yes, I'd agree with all of that. Something that's interesting here with using this combined strong and weak motion database was that this is bringing in a lot of data that we didn't use in developing the ground motion model. Now, it's not an independent test. We clearly do have some degree of overlap. But the data is at least independent data or new data that was not used in the model construction, which is useful, but that benefit is about to be short-lived because we're going to be developing non-ergodic models and we're going to be pulling in absolutely every single piece of data that we can find that's valid. So it won't be independent for very long because, and that's one of the problems behind all this, which is once you start to get more ground motion data, you can't separate out to have independent tests because we want our data to be informing our models. So we can't really and shouldn't really hold anything back, if that's the point. But yeah, I agree, you can't necessarily, you can maybe reject certain outliers if they were to be completely inconsistent with what you've seen. You could throw out certain parts of your model, maybe, with care, but you can't necessarily say that what's left is also valid either.
Okay, I will, Marco.
So I think we are done. So I would like to thank all the participants, of course, the speakers, because I think that we had a lot of very interesting presentations. We had a very good discussion, which was indeed the intent of the workshop. You saw that we kept a lot of time for discussion, for coffee breaks. Hopefully that was an occasion for exchanging ideas and discussing maybe new things. So thanks to European Union and to Metis for giving us the funds to organize this. Maybe there will be another one, who knows, but so, thank you again. And maybe we can take a picture all together just to finish, just to check all the ones that left meanwhile. Thank you again. Yeah, let's take it here, the picture.